Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. At last, we drift in the interstellar ocean, the vast emptiness between the stars. Here the silence deepens even further. The nearest star to our sun is over 4 light-years away, a distance so great that if we continued our journey at the speed of light, it would still take more than 4 years to arrive. In this space, loneliness takes on a new meaning. We could travel for years and not encounter another world or another sun. The darkness is nearly complete, illuminated only by the faint glow of distant stars all around, each an unreachable beacon in a gulf of nothingness. The density of matter here is incredibly low. On average, perhaps a few atoms in an entire cubic centimeter of space. For comparison, a single breath of air contains more atoms than an entire roomful of interstellar space. We are, for all intents and purposes, in a nearly perfect vacuum. Yet even this void is not truly empty. Invisible wisps of gas and dust float here, the remnants of ancient stars and the raw material for future ones. Our sun and its neighbors currently drift through a region called the local bubble, a cavity of hot, thin gas, likely blown by supernova explosions millions of years ago. Within this bubble, the gas is even more rarefied than typical, heated to X-ray glowing temperatures. Eventually, our path will carry us beyond this bubble into slightly denser regions of the galactic medium. We might notice, far ahead, a faint cloud silhouetted against the starry background. As we approach, the stars beyond dim and vanish. We realize we are encountering a molecular cloud, a colossal, cold nebula where starlight is largely extinguished by dust. Inside this cloud, it is nearly pitch black. The gas here is denser, perhaps a few hundred or thousand atoms per cubic centimeter, still a better vacuum than any laboratory on Earth, and far colder, just a few degrees above absolute zero. We are essentially inside a stellar nursery. Deep within, hidden from our view, new stars are being born. We can't see them directly, but if we switch to an infrared view, we'd perceive the faint glow of protostars warming their cocooning gas. Occasionally, one of these newborn stars breaks through its fetal envelope, and its light leaks out, painting the surrounding gas with a ghostly radiance. Perhaps we glimpse a tenuous red emission in a distant part of the cloud, the sign of hydrogen atoms excited by the energetic light of a newborn star cluster. Long, pillar-like shapes may form where young stars' radiation carves the cloud, reminiscent of towers and tendrils of gas silhouetted against the darkness. We drift through this quiet, frigid realm with reverence. Within such clouds, star systems will form, planets will coalesce, and maybe life will one day emerge. Exiting the molecular cloud, we return to the near absolute darkness of interstellar space. The stars crowd more thickly in a band encircling us, the distant glow of our Milky Way's disk. We now realize that we are tiny voyagers in a gigantic galaxy. Around us, here and there, float solitary wanderers, curiosities in the dark. Perhaps we pass surprisingly close to a rogue planet, a world without a sun. It looms out of the black like a silent ship adrift, its surface faintly illuminated by the distant collective glow of the Milky Way. This planet is a frozen, airless rock, or perhaps a cold gas giant. Without the warmth of a star, it has long since gone cold and still. If it has an atmosphere, that atmosphere lies in eternal night, lit only by starlight 1,000,000 times dimmer than the sunlight Earth enjoys. We marvel at this orphan world, one of perhaps trillions that wander the galaxy unbound. For a brief moment, our spacecraft's path intersects the outskirts of its domain, and we detect a whisper of gravity tugging at us, a gentle reminder that even in emptiness, gravity ties everything together. We leave the rogue planet behind, itself oblivious to our passing, continuing into the cosmic dark. There is loneliness here, but also profound serenity, We are more remote now than any human has ever been. In fact, the concept of distance stretches thin in meaning. Home is a barely perceptible point of light lost among millions. The void between stars is so vast that it challenges comprehension. Imagine being in the middle of the Pacific Ocean on a tiny raft with no land in sight. Interstellar space is that, magnified to an extreme. One could travel for centuries and not reach another shore. We feel the scale of our galaxy now not in numbers, but as a physical truth pressing on our soul. The stars are very, very far apart. And yet, this interstellar medium is the connective tissue of the galaxy. The space around us is laced with the echoes of the galaxy's past and the seeds of its future. Cosmic rays, atomic nuclei accelerated to near light speed by distant supernovae, streak through the void, occasionally zipping through our ship and even through our own bodies as silent, invisible bullets. A stray particle of dust, a micron-wide grain that might once have been part of a comet or the atmosphere of a red giant star, drifts by, caught in the very weak currents of galactic gravity and occasional shockwaves from long ago stellar explosions. Every so often, the stillness is disturbed by the faintest murmur of a distant supernova, not in sound, but in the passage of a shell of energetic particles, or a ripple in the galactic magnetic field. These are the subtle languages of the cosmos out here, detectable only with instruments, but present nonetheless. No, interstellar space is not truly empty. It carries the legacy of starbirth and star death. In one region, space may be slightly warmer and ionized, the aftermath of a supernova that blew a bubble of hot gas. In another, it may be cooler and neutral, part of an undisturbed cloud that has floated for eons. We, tiny explorers, find ourselves humbled by this variety and by the enormous scales. 1,000 light years might pass with nothing of note. Then we might cross the edge of a superbubble into a more clouded region where distant stars appear a bit redder due to interstellar dust. The patterns of the galaxy are vast and subtle. Imagine now that we could accelerate further, moving at a significant fraction of the speed of light. Years flash by as we traverse the gulf. Point by point, the constellations around us change. The familiar star patterns of Earth's night sky distort and rearrange as we travel dozens, then hundreds of light years. Stars that were close together from our distant viewpoints separate, and new groupings form. We are like a bird wandering within a giant three-dimensional flock of stars, seeing it from new angles. After about 1,000 light years of travel, we have come so far that the Sun and its nearest companions are now just part of a small haze of stars behind us. We have effectively left the solar neighborhood. Continuing outward, the stars thin out around us as we rise above the plane of the Milky Way's disk. We begin to get a sense of structure. Looking down, we see the Milky Way galaxy in its grandeur. From our new vantage point, a few thousand light years above the galactic plane, the galaxy no longer surrounds us completely. Instead, it spreads out below like a luminous whirlpool set against the blackness of space. The sight is breathtaking. We behold a vast barred spiral galaxy, our galaxy, with its center glowing a warm, dense yellow from myriads of older stars. Cutting through that central glow is a straight bar of stars, a bar that extends on both sides of the nucleus. From the ends of this bar spring the spiral arms, graceful curving trails of light that spiral outward. The arms are not solid arms, but rather patterns of star formation moving through the disk. They are highlighted by blotches of pink and blue. Pink emission nebulae, where new stars are exciting hydrogen gas, and blue clusters of hot, young stars that have recently formed. These arms are mixed with dark patches as well, veils of interstellar dust that block light, appearing as sinuous obscuring filaments. One arm passes near our sun's position, the fragment of a spiral arm we call our Orion spur, a minor arm between major ones. We can see the Sun's location now, about halfway out from the galaxy's center on the inner edge of a spiral arm. The Milky Way's disk is immense, roughly 100,000 light-years across. It is thin relative to its diameter, like a pancake. In its bright starry plane, billions of stars orbit the center, along with nebulae and star clusters. We notice that beyond the bright spiral arms and the central bulge, the galaxy's disk doesn't just abruptly end. It tapers off gradually, with stars getting sparser, but still present out to great distances. A subtle faint disk, thicker and composed of older, dimmer stars, encloses the bright, thin disk. This is the thick disk of the Milky Way, populated by older stars that give off a fainter, warmer glow. It extends a bit above and below the main plane, giving the galaxy a slight thickness. As we continue our outward journey, now essentially upward, relative to the galaxy's plane, the stellar halo comes into view. The halo is a roughly spherical cloud of stars surrounding the Milky Way, far above and below the disk. Unlike the stars of the disk, which orbit in an orderly rotation around the center, the halo stars have more random, elliptical orbits, many of them diving through the disk and back out. They are ancient, some of the oldest stars in the galaxy. We see only a sparse sprinkling of them because they are far apart. However, something else in the halo stands out: globular clusters. These are tight, spherical clusters containing hundreds of thousands of very old stars bound together by gravity. We spot them as fuzzy golden balls of light scattered around the outskirts of the galaxy. Perhaps we recognize a few famous ones. One cluster glitters with so many densely packed stars that its core looks like a continuous glow. These globular clusters orbit the Milky Way's center as well, moving in large, inclined paths, relics of the galaxy's formative years. They hang like lanterns in the deep halo, silently circling. We have now traveled so far out that the entire Milky Way galaxy fits within our field of view. It is a splendid island of light in the cosmic dark. We notice that the galaxy is not isolated. In the distance, we see a few small companion galaxies. Two of them, irregularly shaped and pale, cling near the Milky Way. These are the satellite galaxies, the large and small Magellanic Clouds, though we won't name them here. They are like fluttering moths caught in the gravity of a flame, orbiting our galaxy, and in time perhaps to be absorbed by it. Indeed, streams of stars, tidal streams, can be seen tenuously connecting or encircling the Milky Way, marking where past satellite galaxies were torn apart and incorporated. A bit farther out, we spy a great spiral galaxy, not too unlike our own, but slightly larger. The Milky Way's big sister, the Andromeda Galaxy. Even from our vantage, separated by millions of light years, Andromeda's spiral form is discernible, and its light is a fuzzy patch. We realize that our galaxy and Andromeda are on a slow collision course. In several billion years, these two spirals will fall together, intermixing their stars in a grand embrace. The thought is humbling. The stately pinwheel of the Milky Way, which we just admired, is not a permanent fixture, but part of a dynamic dance of galaxies. Now we drift further out, leaving the immediate vicinity of the Milky Way. We enter intergalactic space, an even more profound emptiness, if such a thing is possible. The distances between galaxies are on the order of millions of light years. The Milky Way shrinks behind us, now just one of countless fuzzy specks in a vast, dark cosmos. As we travel, the pattern of the cosmic web begins to emerge on the largest scales. Galaxies are not scattered randomly. They collect into filaments and clusters. We approach a filament of galaxies, a linear arrangement of many galaxies bound by their mutual gravity and the underlying scaffolding of dark matter. These galaxies are like pearls on a cosmic string, lining up along the filament's length. The filament connects nodes where galaxy clusters reside, enormous congregations of dozens to hundreds of galaxies swarming around a common center. We venture near one such galaxy cluster. Here, the space between galaxies is still vast, but relatively speaking, the galaxies are much closer together than in quiet regions, like where our Milky Way lives. In clusters, galaxies frequently interact and collide. We witness a galactic collision in progress. Two spiral galaxies within the cluster have drawn near each other, their mutual gravity stretching out long tidal tails of stars and gas. Over hundreds of millions of years, which we cannot observe in real time, but we know from simulations and snapshots at different stages, these galaxies will merge. When they do, their spiral structures will be destroyed, and they may form a single large elliptical galaxy, the kind of big, ball-shaped galaxy often found in cluster centers. Indeed, at the core of this cluster, we see a giant elliptical galaxy dominating its companions, a pile of stars likely formed from many past mergers, now a reddish, sprawling system with little gas left to form new stars. It's essentially a galactic city that has grown by consuming neighbors. All around in this cluster, galaxies orbit and interact. Some are spirals with distorted arms from past close encounters. Some are smaller dwarf galaxies, drawn inexorably toward the giants. Clouds of hot gas fill the cluster, undetectable to our eyes, but glowing in X-rays. Gas that has been stripped from galaxies during collisions and now enriches the intergalactic medium with heavy elements forged in stars. The cluster is a crucible of change for galaxies, a place where they evolve rapidly through interactions. Beyond this one cluster, we recognize that it is part of a larger pattern, a supercluster of galaxies linked by filaments. And between these filaments and clusters lie the voids, truly vast regions, tens of millions of light years across, that contain hardly any galaxies at all. These voids are like enormous black cavities, cosmic deserts separating the lush oases of galaxy clusters and filaments. By volume, the voids dominate the universe, yet they are dark and practically empty. Most of the universe is space, just space, with only trace particles and a few stray atoms wandering over unimaginable expanses. We pause in our journey now and take in the panorama of the cosmos. Everywhere we look, there are galaxies upon galaxies. The numbers defy grasp. To give a sense, if you held a grain of sand at arm's length and looked at the patch of sky it covered, that tiny patch could contain thousands of galaxies visible to the most powerful telescopes. There is no empty spot in the sky if your eyes are sensitive enough. Every direction is filled with the faint glow of distant galaxies. Scattered across the darkness like glittering jewels on black velvet, galaxies appear in all shapes and sizes. Elegant spirals, round ellipticals, irregular blobby ones distorted by gravitational encounters, tiny dwarf galaxies barely distinguishable from star clusters. We realize now that our Milky Way is just one of billions, in fact, hundreds of billions or more, of galaxies in the observable universe. Standing here in the gulf between clusters, with galaxies surrounding us in every direction, the scale is staggering. Each galaxy, containing billions or trillions of stars, is itself a universe of possibilities, and there are countless such galaxies. We reflect on the scale of it all. Our entire solar system is an invisible speck. The Earth would be utterly indiscernible, lost in the glare of the sun, which itself is just one modest star in the Milky Way. And the Milky Way is one galaxy among uncounted multitudes stretching for billions of light years in every direction. The light from the most distant galaxies we can see has traveled for over 10 billion years to reach us. We are literally looking into the deep past when we look far away. Light is a time machine. Every photon carries the story of the distance it has traveled. A star 200 light years away shines to us with light that left it 2 centuries ago, around the time of Beethoven and Napoleon on Earth. A galaxy 200 million light years away sends us light that departed when dinosaurs still walked our planet. The farther we gaze, the earlier in time we see. This is one of the universe's great truths. Distance is time. As we observe galaxies billions of light years away, we are seeing them as they were billions of years in the past. The universe at that time was younger, and indeed, those far-flung galaxies appear smaller, more irregular, and often blue with fierce star formation. They are the adolescent galaxies of a younger cosmos, still growing and colliding more frequently. Their shapes are often clumpy or peculiar. Some are in the midst of mergers or rapid starbursts. We are, effectively, watching the universe grow up as we look farther out and back in time. Approaching the horizon of the observable universe, we see the faint glimmers of the first galaxies that formed. They are tiny proto-galaxies, just beginning to coalesce. Their light has traveled almost the entire age of the universe to reach this vantage point. Beyond them, eventually, we reach a point where galaxies did not yet exist. The universe was too young and too hot. If we look beyond even the earliest galaxies, we encounter a glow that comes from all around us. Not from stars or galaxies, but from the universe itself when it was just a baby. This is the cosmic microwave background, the remnant light from the birth of the cosmos. When the universe was about 380,000 years old, infinitesimal compared to its current age of 13.8 billion years, it was a hot, dense plasma of particles and light. As it expanded and cooled, it became transparent, and light was set free to travel. That first light, a blaze of white-hot radiation at the time, has been traveling for almost 14 billion years, stretching and cooling with the expansion of space, and has now become a faint microwave glow coming from every direction. We cannot see it with our eyes, but if we had microwave vision, the entire sky would glow with a gentle cold fire of creation, about 2.7 degrees above absolute zero. These are the most ancient photons, the universe's own afterglow. Embedded in that diffuse glow are tiny ripples, the seeds that would later grow into galaxies and clusters under gravity. We are essentially beholding the cosmic dawn. Beyond this wall of light, the universe was opaque and no light escapes from earlier times. It is the ultimate limit of the observable. Here, at the edge of all we can see, we stop. We are floating in the darkness between galaxy clusters, with the light of billions of years and billions of galaxies surrounding us. We have traveled from the blue skies of Earth to the edge of the universe's visibility. Time and space have been our companions. We have seen the universe in its youth and at its grandest scales. It is time to go home. Gently, we turn our perspective and begin the long journey back inward. Like a camera pulling out of a vast landscape and then zooming in elsewhere, we now retrace our steps. The cosmic web of filaments and voids lies before us like the structure of a great cosmic sponge. We locate the particular filament where our local group of galaxies, the small cluster containing the Milky Way and Andromeda, among others, resides. Moving along that filament, we pass by cluster after cluster, each a swarm of galaxies, until we recognize the slightly quieter neighborhood of our home supercluster. We find the familiar face of the Milky Way galaxy again among its companions. As we draw nearer, the other galaxies of the local group spread out around us. Andromeda, with its spiral arms, the Magellanic Clouds hovering near our Milky Way. We plunge back toward the Milky Way. From above, we see its spiral arms and bar grow larger, filling our view. We angle downward and descend into the disk, like a cosmic diver slipping into a rotating sea of stars. We pass through the stellar halo, whizzing by an ancient globular cluster whose densely packed stars surround us momentarily, like a blizzard of golden snow, before receding into the background. We cross the boundary of the thick disk, where the star density increases. Soon, we are once again amidst the familiar cloudy band of the Milky Way's disk. Star clusters and nebulae dot the scene. The light around us becomes a continuous ocean of stars, the backdrop of the Milky Way that we see as the Milky Band in Earth's sky. We know our sun lies in a quiet region on the inner edge of a spur between the Sagittarius and Perseus spiral arms. We navigate by recognizing nearby stellar landmarks. There is a particular open cluster of young blue stars, the Pleiades perhaps, or another known cluster. A signpost that we are near the Orion arm. We slip into our sun's local stellar neighborhood. The pattern of familiar constellations gradually reassembles around us. Though from our still somewhat removed perspective, they appear slightly out of shape. As we draw within a few dozen light years, the constellations snap back to their familiar look. There, ahead, a yellow star glows with a steady, comforting light. It is average in mass and brightness, unremarkable among the many here, but to us, it is unmistakable: the Sun. Approaching the Sun, we begin to see its family of planets in orbit. The outer planets greet us first. Neptune, a tiny turquoise dot with a faint ring system. Uranus, tilted on its side, a pale green-blue orb. Then the majestic Saturn, encircled by its splendid rings, shining in reflected sunlight. We pass by Saturn's domain, catching a last glimpse of the shadow its rings cast on the planet's cloud tops. Soon Jupiter looms, the giant, with its swirling bands and great red spot coming into view. Perhaps as we sweep past it, we watch one of its large moons casting a black round shadow on Jupiter's cloud surface, a tiny eclipse in progress. We leave Jupiter behind and continue inward, crossing the asteroid belt, still as mostly empty as before. Now the inner solar system unfolds. Mars, glowing faintly red with its deserts and canyons, marks the outer edge of the comfortable zone around the Sun. We skim past Mars, maybe glimpsing the white sparkle of its polar ice cap and the dark stain of an ancient volcanic plateau. Ahead, the Earth appears, a brightening bluish star next to the Sun. As we draw closer, it resolves into a delicate crescent, then a half-lit globe, then nearly full. We watch the Moon, now a familiar companion, orbiting around the Earth, the pair shining together in the sunlight. How vibrant the Earth looks against the black of space. From out here, one can see the blue of its oceans and the white of its clouds swirls clearly. The continents show as golden-green patches. Perhaps it is night on the side facing us. If so, we see the night side sprinkled with the lights of human cities, a golden web across the dark land, shimmering and blinking with life and activity. Perhaps thunderstorms dot the tropical night, flashing silently as they did when we watched from low Earth orbit. The thin atmospheric halo encircles the Earth's circumference, a fragile, glowing line that reminds us how tenuous the boundary between Earth and space is. We descend toward Earth. The blue planet grows until it dominates our view, stunning in its beauty. We slide into the upper atmosphere once more, watching the stars fade behind a growing haze of scattered light. The sky turns from black to deep purple to blue. We feel a gentle tug, the pull of gravity, which never truly left us, but was negligible for so long, now asserts itself as we slow down. Rushing through high, thin air, wisps of clouds racing past, we experience a welcome return of sound, a faint whistle that builds to a roar as the atmosphere embraces us. Parachuting down in our mind's eye, we drift through the tropospheric clouds. Perhaps it is dawn in the place we descend. The horizon is aflame with rosy light, and the shadow of night is retreating westward. Below, the Earth's surface comes into focus, the outlines of coasts, the gleam of sunlight on water, the rich greens of forests or browns of mountains. With a gentle landing, we set foot on the Earth once more. The ground is solid and familiar. We inhale. The air fills our lungs, full of oxygen that plants have made, and we exhale, returning carbon dioxide to the biosphere. In that single breath are also traces of the cosmos, a few atoms of argon that have been part of Earth's air for eons, and even a few ancient photons from the cosmic microwave background, which our lungs do not filter out. Above, the The sky is blue and bright, concealing the stars we visited. The sun shines warmly, and cottony clouds drift in a gentle breeze. Birds might be singing, or a child laughing somewhere, the sweet, ordinary sounds of home that were absent in the mute vacuum of space. Standing here, we reflect on the journey. We traveled from the small, our fragile atmosphere at the edge of space, to the immeasurably large, the cosmic web of galaxies. We experienced the birth of stars in nurseries of gas, and the death of stars in supernova remnants and white dwarfs and neutron stars. Though unseen, they were there in the tapestry. We saw planets adrift without suns, and suns adrift in the gulf between galaxies. We saw that the universe has structure grander than any story ever told, yet it's governed by simple forces that bind atoms into molecules, molecules into dust, dust into planets, planets around stars, stars into galaxies, galaxies into clusters, a hierarchy of connections, an order in the chaos. And most profoundly, we realize that we are part of this story. The atoms that compose our bodies were forged in those distant stars. The iron in our blood, the calcium in our bones, the carbon in our muscles, the oxygen in our lungs, those atoms were brewed in the hearts of ancient stars and scattered through space by stellar winds and supernovae, amn-org. They drifted through the galaxy, became part of the cloud that formed the sun and earth, and ultimately became us. We are literally made of star stuff. We carry inside us a piece of the cosmos's history. Every breath we take links us to the cosmic past, inhaling argon atoms exhaled by dinosaurs and photons that have been traveling since the dawn of time. When we look up at the night sky, the same sky we saw from orbit as a thin glow and from the galactic outskirts as a band of light, we are not looking into a foreign realm. We are looking into our own origins. The water in our veins was perhaps once ice in an interstellar cloud. The proteins that make our skin incorporate nitrogen and sulfur cooked up in supernovae. The light in our eyes as we gaze upward is only made possible by the sun, which itself is a second-generation star, enriched by earlier stars' gifts. Indeed, the very awareness with which we contemplate the universe is a product of the universe itself. Over billions of years, it has evolved the capacity to see and wonder about itself through us. In a profound sense, we are a way for the cosmos to know itself. Our journey outward and back has been at once humbling and elevating. We felt insignificant in the face of galaxies and voids, and yet we also felt transcendent, able to encompass in mind what is physically untraversable in body. Floating in the intergalactic dark, we felt small. But standing here on Earth, we can close our eyes and recall the entire sweep of the cosmos that we have imagined, and realize that in some way, it is contained within us, in our memories, in our consciousness, in the atoms of our bodies that were born out there. Looking around now at the trees, the rocks, and the sky, everything appears as it was, comfortably familiar. And yet, we carry a new perspective. We can whisper to ourselves, in Walt Whitman's words, that a leaf of grass is no less than the journey work of the stars. We have seen that journey work out in the universe, the stars building heavier elements, the galaxies mixing them, the nebulae and planets forming, all leading to a leaf of grass and to us. Outer space is not distant. It is not merely the domain of astronauts and telescopes. It permeates our world and our being. The space that begins where our atmosphere ends extends unbroken all the way to the farthest galaxy and beyond, and we are part of it, woven from its threads. The void between the stars is also the void between the atoms in our bodies. The light of the Big Bang's afterglow gently bathes the Earth even now. The gravity that guides galaxies holds us firmly on the ground. We are connected intimately to the whole. The boundary between Earth and space is a matter of perspective. From the vantage of the universe, there is no boundary. It is one continuous expanse, and we are inhabitants of it. So when we gaze at a starry night, or marvel at a photo from a space telescope, let's remember, we are home. We have always been home. The stars are our ancestors and our descendants. The immense cosmos is not cold and foreign. It is our larger body, our extended family, our collective story. We arrived from it, we live in it, and we will return to it. In the end, stepping back from our extraordinary voyage, we feel a deep sense of belonging. We stand on Earth, perhaps on a quiet hill under a night sky sprinkled with stars, and we feel both tiny and vast, fragile and powerful. We have journeyed to the edges of reality and back on the wings of understanding and imagination. And what we have learned, more than any specific fact or sight, is a simple truth that fills us with peace. Outer space is not distant. It is everywhere. It is in the air we breathe, the ground we walk, the blood in our veins. Outer space is not just above us, it is within us. Outer space is us. Silence, darkness. No stars, no ground beneath your feet, and perhaps not even the flow of time, just an infinite, motionless night. Imagine a void, with no up or down, no sound or motion. In that profound quiet, before anything begins, we find a fundamental question taking shape. What is the dark, yawning space that stretches out in all directions? Not the stars or planets that speckle it, but the space itself. The black canvas on which all cosmic lights are hung. What is space, when it stands alone, empty of all things? Since ancient times, people have looked into the night and pondered the void. Many mythologies begin with a great empty darkness from which creation arises, a cosmic egg in a vast sea, or a formless chaos giving birth to the world. In a way, modern science echoes those old intuitions. We too speak of an initial emptiness that blossomed into the universe we know. We usually imagine space as nothingness, a vacant expanse separating the stars. Even scientists once assumed it was merely an empty stage. In the 19th century, many thought an invisible ether must fill the void, a mysterious medium to carry light. But every experiment to detect this ether failed. Light needed no carrier at all. It moved through pure vacuum. Space, it seemed, could be truly nothing. And yet, if you listen closely to the silence, you may sense something more subtle. The void is not truly void. The darkness is not truly nothing. Space is a presence, an invisible fabric that underlies everything. It is quiet and transparent, so easy to ignore, yet it is real, physical, and dynamic. Space isn't an empty backdrop, but an active, ever-present matrix. It can bend, it can stretch, it can ripple. About a century ago, our picture of space underwent a profound change. Experiments and new ideas revealed that space is not a fixed, unchanging void at all. It can warp and even participate in the cosmic dance. Gravity, we learned, is not a mysterious pull through nothingness, but a bending of space itself by mass. Space and matter interact continuously. Space is like the quiet canvas that holds a painting, or the pause that makes music melodic, an unseen framework that underlies and gives form to everything. Imagine placing a heavy ball on a taut rubber sheet. The sheet stretches and sags under the weight. In much the same way, anything with mass, a planet, a star, a galaxy, presses on the fabric of space. Space curves gently around it. What we feel as gravity is not a pull through emptiness, but the tendency of objects to slide down those curves. The Earth circles the Sun because the Sun dents the space around it, like a large marble sitting on a stretched cloth. Earth is not tethered by invisible strings. It is caught in the Sun's invisible indentation in space-time, moving along a curved path that to us appears as an orbit. In short, mass shapes the geometry of space, and space guides the motion of mass. Even light, which has no mass at all, follows the curves of space. Over 100 years ago, during a total solar eclipse, astronomers noticed that stars appearing near the eclipsed sun were slightly out of place. Their light had bent on its journey to us, detoured by the sun's warped space. It was a dramatic confirmation that space itself, curved by the sun's presence, was guiding the starlight. Today, we regularly use this effect, called gravitational lensing, to observe distant galaxies. A massive cluster of galaxies can act like a cosmic lens, its curved space bending the light of even more distant objects behind it. Sometimes we see a single galaxy smeared into an arc, or even a perfect ring of light encircling a closer galaxy cluster that is acting as the lens. These mirages are the unmistakable signature of space, behaving like a gigantic lens, bending and focusing the paths of light. Through these rings and arcs, we see space itself revealing its curvature to our eyes. If space can bend, it can also stretch. Indeed, the fabric of space has been steadily expanding since the primordial beginning of the universe. Distant galaxies are not just flying away through space. The space between us and them is itself growing. Early observers noticed that the light from remote galaxies is shifted toward the red end of the spectrum, as if the wavelengths have been stretched out. The farther a galaxy, the more its light is redshifted. The straightforward explanation is that space itself is expanding, carrying galaxies apart like raisins embedded in rising dough. Over billions of years, this expansion has enlarged the distances between galaxy clusters immensely. Another useful image is to picture space as the two-dimensional surface of a balloon, with galaxies like ink dots on that surface. As the balloon inflates, the dots move farther apart from each other. No single dot is the center of the expansion. Every dot sees the others receding. Likewise, in our three-dimensional space, every galaxy observes other galaxies rushing away. If we rewind this expansion in our minds, we find that in the distant past, everything was closer together. Galaxies crowd nearer, stars huddle closer. Far enough back, all the matter and light in the universe was crammed into a much smaller volume than today, a state of incredible density and heat. Space itself was compact and blazing with energy. There was a time when the entire young universe was like a hot, glowing fog. Imagine being present in that early inferno. No distinct stars or structures, just a blazing soup of particles and light everywhere you look. An intense white-orange glare filling all of space. As space expanded and thinned out, that searing brilliance faded to a gentler afterglow. Even now, space carries a memory of that fiery beginning. When we point sensitive instruments to the sky, we detect a faint glow of microwaves coming from every direction. This is the afterglow of the primordial fireball, the cosmic microwave background. It is the light from a time about 380,000 years after the Big Bang, when space had cooled enough for atoms to form and for light to travel freely. Since then, those light waves have been stretched by the ongoing expansion of space until they are microwaves, cooled to only a few degrees above absolute zero. Every patch of space is filled with this soft whisper of ancient light. It is almost perfectly uniform and smooth, but has tiny fluctuations, little freckles of slightly warmer and cooler spots, corresponding to minuscule density variations in the early universe. Those slight differences, on the order of only 1 part in 100,000, became the seeds for galaxies and clusters later on. It's as if the walls of the universe still faintly remember their incandescent youth. This ancient light also gives us clues about the overall shape of space. By studying subtle patterns in the microwave background, scientists have learned that on the largest observable scales, space is remarkably flat in its geometry. In a curved universe, those patterns would appear distorted, larger or smaller than expected, much as drawings on a balloon change size when the balloon is inflated. But observations show no such distortion. The angles of those primordial patterns add up just as they would in flat, Euclidean space. For example, in a universe shaped like a 3D sphere, a closed universe, two initially parallel beams of light would eventually converge and meet, and traveling in a straight line long enough could, in theory, loop you around to your starting point, just as an airplane circling the Earth arrives where it began. In a saddle-shaped or open universe, parallel beams would diverge and triangles would have angles summing to less than 180 degrees. But our measurements show nothing of the sort. This suggests that space, as far as we can measure, is not curved into a giant sphere or warped into an endless saddle. Instead, it stretches out in all directions without substantial overall curvature. Space is, to the best of our knowledge, flat and likely unbounded, or so vast that it might as well be infinite. It might extend infinitely, or perhaps it wraps around on a scale so colossal we cannot detect it. But within our cosmic horizon, space behaves like an endless level plane. To achieve such vast flatness and uniformity, the universe likely underwent an extraordinary growth spurt at the very dawn of time. According to the theory of cosmic inflation, a fraction of a second, on the order of 10 over 32 seconds or less, after the Big Bang, space itself expanded at a mind-boggling rate, doubling in size over and over in the blink of an eye. In that brief moment, what had been a microscopic region inflated to astronomical scales. A region smaller than a proton might have stretched to the size of a galaxy in an instant. This rapid stretching would have smoothed out any curvature or clumps, explaining why space now appears so flat and even on large scales. During inflation, tiny random quantum fluctuations, little blips of density in the microscopic early universe, were blown up to enormous sizes. Quantum fluctuations inherent to space itself, magnified to cosmic proportions, became the seeds of future structures. Regions of the young universe that had just slightly more matter or energy became, after inflation, entire huge regions with that slight edge. Those minuscule differences, perhaps only a few parts in 100,000 in density, gave certain patches of space a head start in gravitationally attracting matter. As the universe aged, those patches grew into the first galaxies and clusters. In this way, inflation planted the seeds of cosmic structure. The slight differences from one place to another, once infinitesimal, became the blueprint for all the galaxies, clusters, and voids that would later develop. Space, by expanding so fiercely, essentially cast the dice for the universe's future architecture, turning tiny quantum wrinkles into the grand pattern of stars and galaxies we observe today. When this furious burst of expansion ended, the energy driving it did not simply vanish. It transformed, heating the universe with a burst of radiation and particles. In essence, when inflation stopped, space unleashed its pent-up energy, igniting the hot Big Bang fireball that people often think of as the beginning of the universe. From that point onward, space continued to expand, but at a calmer pace, filled with a blazing plasma that would eventually cool into atoms, gas, stars, and galaxies. The rapid inflationary expansion set the initial conditions, and the slower expansion that followed allowed the cosmos as we know it to emerge. Inflation also opens the door to a startling idea: a multiverse. If the inflationary expansion happened in our region of space, it might have happened, or be still happening, in others. Some theories suggest that inflation never completely stops everywhere. While it ended in our patch, allowing our Big Bang and galaxies to form, in other regions space might still be inflating, or might have ended at a different time. Each of these regions could become its own universe, a bubble with its own galaxies, and perhaps even different physical constants. Our observable universe would then be just one bubble in a limitless foaming sea of universes. We have no way to directly see these other bubbles. They lie beyond any light we could ever receive. But the multiverse concept shows how our conception of space may extend even beyond the bounds of our own universe. Space, in this grand view, is an ever-expanding ocean, spawning countless cosmic islands. Whether this is true or not remains speculative, but it stretches our imagination of what space could be, not just the stage of one universe, but perhaps a prolific generator of many. Over billions of years following inflation, gravity worked on the tiny density variations left in the fabric of expanding space, drawing matter into clouds and clumps that would ignite as the first stars and galaxies. Galaxies pulled together into groups and clusters, and these linked up via filaments of gas and dark matter, forming a vast cosmic web. On the largest scale, the universe looks like a spider web or a sponge, dense clusters of galaxies connected by thread-like filaments, with enormous dark voids in between. Those voids, immense bubbles, millions of light years across, nearly empty of galaxies, are the regions that gravity emptied out as it drew matter into the filaments. In other words, most of the universe's volume consists of these yawning voids, with the galaxies tracing lacy patterns along their boundaries. It's a breathtaking structure, the invisible scaffolding shaped by gravity out of the expanding fabric of space, with over 80% of the volume of the universe contained in those silent voids. The lights of the stars and galaxies stand out like glittering nodes, but it is the darkness between them that dominates by volume. Now picture yourself in the middle of one of those cosmic voids, utterly removed from any galaxy. You are floating in intergalactic darkness, light years from the nearest star. Around you, the darkness is nearly absolute. Perhaps a faint, ghostly smudge of a distant galaxy is barely visible in one patch of sky, and another dim glow in the opposite direction. But to your unaided eyes, it would mostly be pure black. The nearest substantial galaxy could be tens of millions of light years away, so far that its light is unimaginably feeble. You are, for all practical purposes, alone in a silent, endless night. This is space at its most austere, a volume of the universe almost entirely devoid of matter. And yet, even here, space is not truly empty. A stray hydrogen atom might drift by now and then, or a thin breeze of particles from some far-off galaxy cluster might waft through. You would also be bathed in the ever-present microwave background radiation from the Big Bang, though you wouldn't sense it without instruments. In this void, you can viscerally feel that space is something real, a vast container with you at the center and almost nothing else around. It's a haunting, beautiful solitude. Such voids are the dark wombs of the cosmos, within which the bright filaments of the cosmic web are suspended. Gravity's architecture, the cosmic web of filaments and voids, is heavily influenced by a form of matter we cannot see, dark matter. Decades ago, astronomers measuring the speeds of stars in galaxies discovered a surprise. In galaxies like our Milky Way, the outer stars orbit the center far faster than expected, based on the visible stars and gas alone. They should have been flung off into space, but they remained bound. It was as if an extra unseen mass was providing the gravitational pull to hold them in. Likewise, galaxies in rich clusters move as though there is much more mass present than we can account for with the observed galaxies and hot gas. And when we observe gravitational lensing by a cluster, the bending of light is far stronger than visible matter alone can explain. All of this evidence points to a vast amount of invisible mass enveloping galaxies and clusters. We call this mysterious substance dark matter. It neither emits nor absorbs light, making it effectively invisible to our telescopes. Yet it outweighs ordinary matter by a factor of about 5. Dark matter forms huge halos around galaxies, extending well beyond the visible stars. Every galaxy, including our own, is embedded in a cocoon of this invisible material. Entire galaxy clusters are swathed in massive clouds of dark matter. Its gravity is what helped pull normal matter into the filaments of the cosmic web in the first place. Without dark matter's guiding gravitational pull, the universe's large-scale structure would have formed much more slowly and differently. We cannot see dark matter directly, but we see its imprint. Space curves around it, and galaxies move under its gravitational influence. Through these effects, the hidden scaffolding of dark matter in space becomes perceptible. Space is quietly filled with an unseen mass that shapes the universe profoundly. In the late 20th century came another revelation. The expansion of space is accelerating. After gravity built the cosmic web, one might expect that over time the pull of all those galaxies on each other would slow the expansion of space. And for billions of years, it likely did slow. But to great astonishment, we have found that in the last few billion years, the expansion of the universe has begun to speed up again. Distant galaxies are receding faster and faster as time goes on. Space is expanding not only steadily, but with an ever-increasing pace, as if some mysterious force is pushing it outward. We give the name dark energy to this unknown cause of cosmic acceleration. Unlike dark matter, which adds gravity, dark energy seems to act as a kind of anti-gravity on vast scales, a subtle pressure embedded in the fabric of space that drives it to expand faster. As space grows, more of this repulsive effect appears, since dark energy is thought to be a property of space itself, pushing galaxies apart with increasing strength. Today, dark energy dominates the universe's energy balance. Roughly 70% of the total contents of the cosmos appears to be this shadowy influence, with dark matter making up most of the rest. The ordinary matter, the stars, gas, dust, planets, and us, accounts for only a few percent. In an ironic twist, the emptiest thing, space, contains the majority of the universe's energy in this form. The silent void has an energetic underpinning that shapes the cosmos. What this means for the far future is profound. As space expands faster and faster, galaxies that are now visible will eventually slip beyond our cosmic horizon, their light stretched and diminished until they vanish from view. In tens or hundreds of billions of years, everything outside our local group of galaxies will have moved out of reach. The universe will appear to whoever remains as an empty void, with only the local galaxies, perhaps merged into one, in view. For example, in about 100 billion years, the galaxies of the Virgo cluster and beyond may be so far that their light never reaches the Milky Way region. After many hundreds of billions more years, even the nearest large galaxy, Andromeda, now destined to collide and merge with our Milky Way long before then, and its remnants would be far beyond detection. The expansion of space will carry all other islands of matter irretrievably away. What will the cosmos look like then? In that deep future, the observable universe will become dark and empty, with only faint whispers of local starlight remaining. Perhaps an astronomer living in that far future era on some distant world would peer into the sky and see nothing beyond her own galaxy. She might point her telescope outward and find endless blackness in every direction. All other galaxies would have faded beyond reach or redshifted into obscurity. She would have no way of knowing that a vast cosmos full of galaxies had ever existed. The cosmic truth we know today, that space teems with billions of galaxies, would be hidden from her by the relentless expansion of space. That future astronomer might conclude that her galaxy was the entire universe, a tiny island adrift in infinite nothingness. For us living in the present cosmos, the discovery of dark energy is a humbling reminder that what we once took to be empty nothingness can control the destiny of everything. The silent space between galaxies turns out to hold a secret power that shapes the entire evolution and future of the universe. Space, the quiet stage, has proven to be the hidden protagonist of the cosmic story. Before we return home, let us take an imaginary journey back through the cosmic expanse. Picture yourself out at the edge of a great cluster of galaxies, where hundreds of galaxies shimmer around you like a glittering swarm. Now you begin to travel back toward our own galaxy. As you move, galaxies drift past, scattered in the vast darkness. You glide along one of the filaments of the cosmic web that leads to the Milky Way, passing other island universes along the way. In the distance ahead, a faint band of light comes into view, the combined glow of billions of stars. Our Milky Way, seen from afar as a hazy, spiral disk of light. You approach it, crossing the immense gulf of intergalactic space. Now you plunge into the outskirts of our galaxy, rushing past sparse outer star clusters and the wispy halo of tenuous gas. The star density increases around you as you enter the Milky Way's disk. Entire clusters of young stars drift by. Great nebulae, stellar nurseries, glow softly in pink and blue. By the time you near the inner regions, stars surround you like a sparkling ocean. You weave through a spiral arm, passing magnificent blue-white giants and red supergiants, skirting around clouds of interstellar dust. In the distance, you spot a modest yellow star, our Sun, coming into view. As you draw closer, you see it is accompanied by planets orbiting in the plane of a thin, flat solar system. You sweep past the orbit of Jupiter, then Mars, and now the blue sphere of Earth appears. At this scale, it is a tiny, fragile-looking bead of blue and white, shining against the blackness. You home in on it, watching its oceans and clouds resolve into clarity. In moments, the planet looms large, its atmosphere a glowing thin shell. You slip gently into that atmosphere, experiencing the rush of air as you descend, and finally come to rest on Earth's surface, back to the soft familiarity of ground beneath your feet. Your fantastical voyage from the end of the universe to our home is complete. Now, having roamed the vast reaches of the cosmos, let us gently return our focus to something more intimate, the space around and within us. We leave the clusters of galaxies and zoom back toward a single galaxy, our Milky Way, and then to a particular star, our Sun, with its family of orbiting planets. Between those worlds stretches millions of kilometers of space, populated only by sparse dust and the thin wind of charged particles from the Sun. Closer in, we see the blue marble of Earth, surrounded by the gauzy blue halo of its atmosphere. From high above, Earth appears as a delicate blue-white sphere hanging in the blackness. Our atmosphere, a thin film of air and cloud, clings to its surface and gradually merges into space. Only a few hundred kilometers up, the air becomes so tenuous that space begins. Beyond that, the sky fades to black. In truth, there is no sharp boundary where space starts. The air just thins more and more until there is effectively none. But effectively, just above the blue sky, the true vacuum of space begins. Only a fragile veil of atmosphere separates us from the cosmic void. There, in low Earth orbit, astronauts aboard space stations witness directly the stark contrast between the bright Earth below and the utter blackness above. They float in microgravity, essentially falling around Earth, immersed in space. When they look up, away from Earth, they see endless darkness spotted with stars that do not twinkle because there is no air up there to flutter their light. The sun shines fiercely without the softening filter of atmosphere, and the divide between day-lit Earth and night-shadowed Earth is a sharp line across the globe. Those astronauts live on the very boundary of space, inside a thin bubble of air in their spacecraft that separates them from the vacuum outside. They often describe the experience as deeply humbling. Above them, an infinite void. Below them, the jewel of Earth with its thin blanket of air. During spacewalks, when they step outside into the vacuum, wearing only a protective suit, they can feel the profound silence and isolation of space. No sound, no breeze, only the distant curve of Earth and the raw, brilliant stars. For them, space is not a theoretical concept, but a palpable reality. They understand in their bones that space is here, around us, an ever-present ocean, just a breath beyond our daily reach. We descend back to the surface now. Picture yourself standing on a quiet night field, looking up at the stars. Although you feel solid ground underfoot and air on your skin, you are as much in space as an astronaut floating in orbit. The space around you is simply filled with a thin mixture of gases, our atmosphere. If you could magically remove all that air, the vacuum that remains would be continuous with the vacuum between the planets and stars. There is no wall or border between space down here and space up there. It is one connected expanse. The same space that stretches between galaxies is present in the room around you, between the walls and among the molecules of air. We truly have never left space. We live at the bottom of a shallow ocean of air, but that ocean is itself embedded in space. People often talk about going into space as if it's somewhere else, but space is already here, step by step. As you climb a mountain or rise in a balloon, the air thins and space reveals itself. Astronauts in orbit are not in a different realm. They have merely ascended above most of the air, into the naked vacuum that was there all along. Space is not distant. It is the backdrop of our existence, even here on Earth. Even our everyday experiences are dialogues with space. Take a breath. You inhale molecules of air that moments ago were scattered across the room, and you exhale molecules that will disperse outward. In doing so, you are stirring the space around you. The air filling your lungs quickly mixes and returns to the atmosphere, ultimately diffusing into the great expanse. In a very real sense, space is the medium through which life interacts with the world. Every movement you make is a displacement in space. Every sound you hear travels to you through vibrating molecules in space. Out in the near-total vacuum beyond Earth's atmosphere, there is no air to carry sound. In space, no one would hear you scream. It is truly silent out there. Every sight you see is brought to your eyes by light crossing space. Space is not an abstract backdrop to life. It is intimately involved in every aspect of our being. Consider even more deeply, you yourself are largely made of space. The atoms in your body are mostly void, their mass concentrated in tiny nuclei, and their size defined by electrons moving through emptiness. If all the empty space in your atoms were somehow removed, you would collapse into a speck far too small to see. And of course, without that space, you wouldn't exist as a living being at all. It is the spacious architecture of your atoms that allows them to bond into molecules, and molecules to build cells, and cells to form a living organism. Thus, space is inside you as much as you are in space. It provides the room that your particles and forces need to operate. We begin to see a pattern from the vast distances between galaxies down to the tiny gaps within atoms. Space is there, quietly doing its work. It provides room for structure to exist, for planets to orbit, for light to travel, for atoms to join and form molecules. The emptiness is not a flaw or an absence. It is an essential ingredient. It allows separation and form. Without the gulf of space within each atom, there could be no distinct atoms and no chemistry, no solid matter as we know it. Without the reaches of space between stars, gravity could not isolate individual worlds where life might arise. Space is the great enabler, the silent canvas that allows matter to take shape and motion to have meaning. Just as a clay pot's usefulness lies in the empty space it encloses, the utility of the cosmos lies in its gaps and hollows. An empty cup holds water. The emptiness within an atom allows it to bond with others. In both cases, what is not there enables what is there to function. And what about space at even smaller scales, far smaller than an atom, smaller than the tiniest subatomic particle? Here we approach deep mysteries. Physicists suspect that if you zoom in far enough, space itself becomes turbulent and uncertain. On the scale of the Planck length, about 10 to 35 meters, the very concept of distance might break down. space might dissolve into a kind of quantum foam, with the smooth fabric of space-time becoming frothy and indeterminate. At that scale, according to some ideas, tiny bubbles of space-time could appear and vanish, and geometry itself might fluctuate wildly. Wheeler, a physicist, famously imagined the scene as the quantum foam, a churn of space-time at the smallest scales. Over sufficiently small distances and brief moments, the smooth geometry of space and time could erupt into a storm of random fluctuations. Imagine zooming into what looks like a smooth photograph, only to find it grainy with pixels at a certain magnification. These fluctuations could be large enough, on those scales, to cause significant departures from the smooth space-time we perceive at human scales, giving space a foamy, jittering character when examined ultramicroscopically. With our current technology and understanding, we cannot probe such minute scales directly. Our best theories, quantum mechanics and general relativity, don't play nicely together at this extreme, so we don't yet have a clear picture of what space truly looks like at the Planck scale. It's possible that space-time is not fundamentally smooth. It might be made of countless tiny units or threads. There is no definitive reason that space needs to be perfectly continuous. Perhaps, in a full theory of quantum gravity, space-time would consist of many small, ever-changing regions where space and time themselves blur and fluctuate. It's a mind-bending idea. The familiar continuity of space might, under magnification of 1033, break into a ceaseless fizz of tiny distortions and ephemeral particles popping in and out of existence. Yet black holes are not absolutely black. Quantum theory predicts that the vacuum near the event horizon of a black hole seethes with particle-antiparticle pairs. Occasionally, one particle from such a pair can be pulled into the black hole while the other escapes. To an outside observer, the black hole appears to emit a faint trickle of particles, a phenomenon known as Hawking radiation. Over inconceivably long periods, this process can cause a black hole to slowly evaporate, leaking its mass back out into space. This is another reminder that even the empty space near a black hole is full of activity. The vacuum isn't void at all. Its quantum fluctuations can have tangible effects, bleeding away the black hole's mass bit by bit. In this way, space acts as both giver and taker, swallowing light at the horizon, yet furtively returning energy to the universe through quantum processes. One place where we suspect this quantum nature of space becomes crucial is inside black holes, those mysterious abysses formed from collapsed stars. A black hole is a region where space is curved so extremely that once anything, matter or light, falls in, it cannot escape. The boundary around a black hole is called the event horizon. At that boundary, space is rushing inward at the speed of light, like a waterfall of space-time cascading into the hole. If you approach the horizon, time slows relative to the outside world, and the pull of gravity, the curvature of space, becomes overwhelming. To a distant observer, you would appear to slow and dim, never quite falling in, as your final light waves get stretched and weakened, a strange visual consequence of the way space and time warp. Beyond the horizon, all paths lead further inward, deeper into the hole. As you fall inside a black hole, you would experience space rushing you inexorably toward the center. According to general relativity, at the very center lies a singularity, a point of infinite density where space and time, as we know them, ends. In truth, this singularity is likely where our current understanding fails. Gravity is so extreme and the scale so tiny that quantum effects should dominate. Here, the smooth fabric of space might tear or blend with the quantum foam. The distinction between space and matter could blur. We don't yet have a theory of quantum gravity to tell us exactly what happens in such an intense intersection of the very large and the very small. Does space cease to exist as a meaningful concept at the core of a black hole? Are there atoms of space-time or quantum threads knitting things together beyond our view? We simply don't know. The laws of physics as we have them break down in these conditions. Physicists have proposed bold ideas to reconcile these deep conflicts. One radical suggestion is that space and time might not be fundamental at all, but rather emerge from something more basic and abstract. Some research hints that quantum entanglement, the ghostly interconnection between particles, may knit together the fabric of space itself. In certain theoretical models, the geometry of a region of space can be described entirely by the information, the entanglement connections, on its boundary. This is known as the holographic principle, suggesting that our three-dimensional space might in some way be a projection from information encoded on a distant two-dimensional surface. It's as if space could be woven from quantum threads of information. Another idea is that space-time is composed of tiny, discrete units, sometimes envisioned in approaches like loop quantum gravity, so that on the smallest scale, space is more like a woven lattice or network. These concepts are still speculative and hard to test, but they share a poetic point. They hint that space, for all its apparent continuity, might be an emergent illusion, like a tapestry that looks smooth from afar, but up close is made of fine threads. If so, there could exist degrees of freedom or building blocks of the universe more fundamental than space and time. What is space, truly? It may be that our familiar space is just the visible frosting on a much deeper reality. Facing these profound questions, humanity has responded by inventing clever ways to probe the nature of space. We have built powerful telescopes that peer across billions of light years, effectively allowing us to look back in time and see the young universe when it was filled with hot plasma and newly formed galaxies. We have launched observatories above our atmosphere to measure the cosmic microwave background with exquisite precision, mapping its faint ripples to decode how space expanded and what it contains. We have devised experiments on Earth to test the nature of the vacuum. For instance, sensitive laboratory apparatus has confirmed the Casimir effect, detecting the slight pressure of vacuum fluctuations pushing two plates together. We smash particles together in giant accelerators, momentarily concentrating tremendous energy into tiny volumes of space, to glimpse how nature behaves at the highest energies and smallest scales. This endeavor led to the discovery of the elusive Higgs field that permeates space and endows particles with mass. We have even detected the subtle ringing of space-time itself using gravitational wave observatories like LIGO. These giant laser interferometers can sense when space stretches and squeezes by less than a trillionth of a centimeter as a gravitational wave passes. The first such detection in 2015 came from two merging black holes and was heard as a faint chirp, literally the sound, after conversion, of space briefly vibrating from a cosmic collision. Since then, we have caught multiple cosmic events via gravitational waves, black holes swallowing each other, neutron stars colliding and sending tremors through space. It's a completely new way of listening to the silent universe, using space itself as our messenger. We have also physically journeyed into space, albeit only a small distance so far in cosmic terms. Our robotic probes have ventured beyond the planets, sampling the environment of space directly. The Voyager 1 and 2 spacecraft, for example, have traveled beyond the influence of our sun's solar wind and entered interstellar space, the space between the stars. They confirmed that even the emptiest regions of our galaxy are not entirely empty. They contain traces of very thin plasma, ionized gas, and high-energy cosmic rays. Voyager 1, now over 23 billion kilometers away, is humanity's farthest messenger. It is sailing through the cold, silent void, reporting back that even out there, far from any star, there are a few atoms per cubic centimeter and faint whispers of magnetic fields and radiation. Its journey reminds us that space is not a distant void we go to. It's the ocean we've always been swimming in, now stretching out to greater and greater depths. We are not outsiders to the universe's expanse. We are an integral part of it. We move through space, we depend on it, we are composed of it. In a sense, we, conscious beings, are space's way of observing itself, the universe contemplating its own vastness through our eyes. From the space between galaxies to the space inside your chest, it is one continuous fabric. The next time you gaze up on a clear night and marvel at the darkness between the stars, remember that that darkness is not empty. It is the same space that cradles you, extending through and around you always. We tend to think of ourselves as down here and space as out there. But in truth, we have always been in space. From the moment of our birth, we have been enveloped by space. Space is not a distant domain only astronauts visit. It is the vast, subtle medium in which we live and breathe. When you look up at the night sky, you are looking into an extension of your own surroundings. The air ends not far above your head, and then space continues, unbroken, to the ends of the universe. So, what is space? It is not a mere nothingness, not a sterile void. It is the gentle scaffolding that holds all of creation. It is a medium that can bend and ripple, a vast field that carries light and nourishes the formation of stars. Space is the silence that allows the music of existence to be heard. It is the canvas on which the galaxies are painted. And yet the canvas itself has texture and influence beyond what our eyes see. Space is the invisible architecture of the universe, the foundation that connects all things. It is often said that nature abhors a vacuum, but in truth, nature uses the vacuum, space, as the foundation for everything. Without space, there would be no room for light to travel, no separation for objects to exist apart, no time for events to unfold. Space is not the absence of things. It is the presence that allows things to be. It is the very possibility of anything and everything. As our journey through darkness and light comes to an end, we return to that initial quiet question and find a profound answer. Space is not an emptiness to be feared, but a presence to be revered. It is the quietly fertile nothing that makes everything possible. We float in it, we are made of it, and we are forever embraced by it. The invisible architecture of the universe surrounds and sustains us. Space is the darkness that cradles the stars, the silence that gives meaning to sound, the stillness that makes motion possible. It is the vast, living fabric in which the story of the cosmos and our own story is written. Space is the womb of the universe, the canvas of creation. It is not an absence, but the gentle yet all-encompassing presence that allows all things to be. Before time, before space, there was nothing. Not darkness, not a void in which something could drift, for even darkness and emptiness require a place to exist. It was a nothingness beyond comprehension, a silence so absolute that no thought or word could pierce it. In that great silence before creation, no light shone, no sound echoed. All the energies and forces we now know were dormant or absent, in a state that defies human language. It is the canvas of non-existence upon which our cosmos would one day be painted. What does it mean to be born from nothing? This question has haunted philosophers and scientists alike. In ancient myths, the world emerges from chaos, from a giant cosmic egg or the spoken word of a deity in the void. These are human attempts to grapple with the ultimate mystery, how something, the universe, reality, everything we know, could spring into being when there was no before, no bedrock of space or time. In the beginning of our scientific story, there is a similar mystery. The equations of physics whisper that time and space themselves began in a stupendous moment, leaving no trace of a prior era for us to read. If there was a before, it lies hidden behind a veil we cannot yet lift. One idea is that time itself began with the birth of the universe. Asking what came before might be as meaningless as asking what lies north of the North Pole. Another idea suggests our universe is one cycle in an eternal series, that the silence before the Big Bang was the echo of an earlier cosmos that ended, and from its demise, our own was born. In this view, nothingness might be more like a cosmic pause between breaths, the universe exhaling and inhaling over infinite eons. But these are speculations at the edge of knowledge. What we know is that roughly 13.8 billion years ago, the silence ended. Out of the void, a flash of creation erupted. In an immeasurable fraction of a second, the universe began. It burst forth from perhaps an infinitesimal point, smaller than an atom, with unfathomable energy. All the matter, energy, space, and time that now exists was concentrated in that embryonic cosmos. The nothingness, whatever it truly was, gave way to a fierce and blazing emergence. The universe was born from nothing in the sense that no pre-existing space cradled it. It made its own space, it made its own time. That first moment was not a normal explosion in space. It was an explosion of space itself. Silence was replaced by a roar of creation, though there were not yet ears or air to carry sound. Darkness was replaced by a searing burst of light, though in truth, the infant universe was so hot that light was immediately trapped, tangled with matter. Still, we speak in metaphors because our minds need them. We imagine a great cosmic dawn breaking over an infinite expanse of nothing, heralding the start of everything. In reality, that dawn was everywhere at once, and the expanse itself was just coming into existence. From absolute silence and emptiness came a thunderous birth. In the first instance, the universe was a tempest of unimaginable energy. Time and space had just unfurled, and everything that would ever be was compressed into an inconceivably dense state. The temperature was so high that the known laws of physics melded together. Forces that today are distinct, gravity, electromagnetism, the forces that bind atomic nuclei, were unified in that newborn moment. There were no atoms, no particles as we know them, only a furious blur of pure energy. Then, in a brief flash of less than a trillionth of a second, something extraordinary happened. The universe underwent a growth spurt unlike anything since. We call this moment cosmic inflation. It may have been triggered when one of the fundamental forces, the strong nuclear force, snapped free from an earlier unified state, releasing an enormous energy that drove space to expand exponentially. Space itself expanded at a staggering rate, far faster than the speed of light. This did not violate any cosmic speed limit. Rather, it was space carrying matter along, stretching the very fabric of reality. In that infinitesimal blink, the universe grew from smaller than a subatomic particle to perhaps the size of a grapefruit or larger. To an outside observer, if one could exist, it would have looked like nothing one moment and an entire nascent universe the next. But there was no outside yet, for space itself was young and expanding. Why did inflation occur? What drove this wild expansion? These questions remain on the cutting edge of cosmology. Perhaps an exotic form of energy in the vacuum triggered it, a high-energy state of empty space that suddenly released its energy into the expansion of space. As inflation raged, it ironed out any irregularities. Just as a balloon, when blown up, smooths out its wrinkles, the inflating cosmos became extremely uniform. Any curvature or clumps were stretched thin. Distant regions that could never have contacted each other under normal expansion were, just moments before, intimately close together. Inflation flung them far apart, bestowing the universe with vast size and an almost featureless consistency. Almost, but not entirely featureless. Even in the raging furnace of the very early universe, randomness played its part. The quantum world, with its jittery, unpredictable fluctuations, left faint imprints on the density of that primordial energy. Tiny flickers, slight differences in density and temperature originating from the quantum foam of existence, were trapped and amplified by inflation. As space ballooned, those minuscule fluctuations were stretched to astronomical scales. Where there was ever so slightly more energy in the microscopic chaos, now there was a denser patch of universe. Where there was slightly less, a thinner patch. These differences were unimaginably small, mere 1 part in 100,000 deviations from perfect uniformity. Yet they were profoundly important. In time, those tiny wrinkles in the otherwise smooth cosmos would grow into galaxies, clusters, and great cosmic structures. In essence, cosmic inflation took quantum whispers and made them the blueprint for the stars and galaxies we see today. The inflationary burst was over almost as soon as it began, a fleeting cosmic heartbeat of expansion. When it ended, the energy driving it did not simply vanish. Instead, like a wound-up spring suddenly released, that energy transformed into an immense bloom of particles and radiation. The universe reheated. In that moment, what we typically think of as the Big Bang, a hot, dense explosion of matter and light, occurred. Space became filled with a high-energy plasma, a hot soup of particles. In that newborn fireball, matter and energy were interconvertible. Particles were created and destroyed incessantly. Quarks, electrons, antiquarks, positrons, photons, neutrinos, all kinds of exotic, fleeting particles roiled in a searing broth. Protons and neutrons did not yet exist as bound states. Instead, their constituents, quarks and gluons, swarmed freely. The temperature was on the order of billions upon billions of degrees. Matter and antimatter were being forged in almost equal measure, only to annihilate back into light. For every billion matter-antimatter pairs that annihilated, a tiny bit of matter, perhaps one particle, survived without a partner. That vanishingly small excess of matter was enough to ensure that our universe would not end up empty. It would become the stuff of stars and life. The universe almost became nothing again through mutual destruction, but thanks to that slight imbalance favoring matter, something remained. A few grains of matter per immense volume of energy, the seeds from which all galaxies, stars, and planets would later form. As fractions of a second turned into whole seconds, the universe continued to expand, though at a gentler pace than inflation's mad rush. With expansion came cooling. By the time the universe was 1 second old, it had cooled to billions of degrees and was still filled with a dense plasma of particles and radiation. In that first second, the basic forces of nature settled into their separate identities. Gravity had split off earliest, during inflation. Now the strong nuclear force and electro-weak force had also separated into the forces we know today: strong, weak, electromagnetic. The stage was set for the next steps in cosmic evolution. Amid this churning plasma, something else important happened in those first seconds. Neutrinos, ghostly, nearly non-interacting particles, decoupled. These wisps slipped out of the dense throng and began streaming freely through space, barely impeded by matter. The universe became transparent to neutrinos almost immediately, at around 1 second old. Those neutrinos still travel today as an all-pervasive cosmic neutrino background, a silent kin to the light that would later be set free. They are hard to detect, but they remain one of the surviving whispers of the infant universe. The embryo universe, still less than a minute old, was immensely hot and bright. Quarks had begun to combine into triplets, forming the first protons and neutrons within the first millionth of a second, once the universe cooled below roughly 1 trillion degrees. Now, as time passed the mark of a few seconds, the frenetic particle-antiparticle annihilation ended. Most antimatter had paired off and disappeared in a flash of gamma rays, leaving that tiny surplus of matter. A sea of photons, light particles, dominated the energy content, but there were also countless neutrinos, and a growing number of protons, neutrons, and electrons, the raw ingredients of atoms, though not yet assembled into atoms. As the newborn universe moved from its first seconds into its first minutes, it continued to cool and expand. The frenetic collisions of particles began to slow just enough for new kinds of order to emerge. Around 3 to 4 minutes after the bang, the temperature fell to about 1 billion degrees, roughly 70 times hotter than the core of the Sun. Now atomic nuclei could begin to form. Protons and neutrons, freshly forged from quarks, found the universe cool enough to stick together under the embrace of the strong nuclear force. A second great creation event unfolded in this period. Big Bang nucleosynthesis, the formation of the first atomic nuclei. In the blazing furnace of these early minutes, protons slammed into neutrons and fused. Helium, the second simplest element, began to form in abundance. For a brief window of time, conditions were just right for nuclear fusion on a cosmic scale. Much as the cores of stars billions of years later would fuse hydrogen into helium, the entire young universe functioned like a star, converting the simplest elements into slightly heavier ones. Over about 17 minutes, most of the neutrons in the universe, which are unstable on their own and would decay if left isolated, managed to fuse into helium nuclei, each consisting of 2 protons and 2 neutrons, or a few other light nuclei. By the time this period ended, about 25% of the mass of ordinary matter had become helium nuclei, with the remaining 75% remaining as hydrogen nuclei, single protons. A trace of deuterium, heavy hydrogen, and lithium, with 3 protons, also formed. The universe's initial chemical makeup was set: predominantly hydrogen, a healthy dose of helium, and tiny traces of lithium and beryllium. After about 20 minutes, it had expanded and cooled too much for further fusion. The furnace of the Big Bang's beginning flickered out. At this point, the universe was still an extremely hot plasma. Imagine an extremely dense, opaque fog of charged particles, electrons, nuclei, and photons. It was as bright as the interior of a star, but no light could travel very far. Space was like a brilliant, blinding mist. Any photon, particle of light, that tried to go more than a tiny distance would smack into a free electron and scatter. The universe was opaque, a glowing fog of light and matter tightly coupled. To an imaginary observer floating at, say, 100,000 years after the bang, the surroundings would look like a uniform glow, as if you were embedded in the surface of a star. You wouldn't be able to see through it. The concept of distance beyond a certain point had no visual meaning because light hadn't yet broken free. The cosmos was radiating, but curtained by its own dense matter. However, the expansion continued, and with it came cooling and thinning of that particle soup. Thousands of years passed, then tens of thousands. During this epoch, the energy of the universe was dominated by radiation, light, which kept matter particles flying apart and resisted gravity's efforts to clump things together. But gravity was patiently tugging on the matter nonetheless, and as the universe grew, the density of radiation fell faster than the density of matter. About 50,000 years in, matter took over as the dominant component controlling the dynamics of the universe's expansion. The radiation era gave way to the matter era. This meant that at large scales, gravity now had the upper hand to start drawing matter together into the seeds of galaxies and clusters, though it would still be some time before these structures became pronounced, since everything was still mixed in the hot plasma. Fast forward to approximately 380,000 years after the Big Bang. The temperature had fallen to around 3000 K, about the surface temperature of a cool star, roughly an orange glow. At this point, something profound occurred. Electrons began to combine with nuclei to form neutral atoms. A proton capturing an electron makes a hydrogen atom. Helium nuclei capturing electrons make helium atoms. This process is called recombination, though it's really combination for the first time. With most electrons suddenly bound into atoms, they were no longer free to scatter photons at every turn. The cosmic fog lifted. The universe became transparent. It was as dramatic as night turning into day on a cosmic scale, except here it was a bright, hot fog turning into clear darkness. For the first time, light could travel great distances without being immediately absorbed or deflected. When the cosmic fog cleared, the light that had been trapped was released to fly freely through space. The universe was about 380,000 years old, and this was its first free streaming light, often called the first light of the cosmos. The entire sky everywhere would have glowed with a bright, warm radiance. If human eyes had existed then and could survive the conditions, they would have seen a soft, orange-white glow coming from all directions, like being in the middle of a vast glowing cloud. That glow was the combined light of the hot plasma, suddenly unleashed. As the universe expanded over time, this flash of light lost energy and shifted to longer wavelengths. What started as an intense orange-white glow stretched into a dimmer red, then into the infrared, and eventually, over billions of years, into the microwave part of the spectrum. Today, we detect this primordial light as the cosmic microwave background, CMB, a faint afterglow permeating the entire universe. The CMB is the oldest light we can see, a messenger from the cosmic infant years. It is extraordinarily uniform, with a temperature of about 2.725 K, just 2.7 degrees above absolute zero in every direction. Yet, it's not perfectly uniform. There are tiny variations in its temperature, only tens of microkelvins different, 1 part in 100,000 of difference. These subtle freckles in the CMB are the direct imprints of the quantum fluctuations from the time of inflation, imprinted on the matter distribution when the universe was young. Regions that are a hair hotter in the CMB correspond to slightly denser areas back then. Slightly cooler spots correspond to slightly less dense areas. These differences are only a fraction of a percent, but they are crucial. Over time, gravity will amplify those slight over and under densities into the cosmic structures we see today. When we map the CMB, as satellites like COBE, WMAP, and Planck have done, we are effectively seeing the seeds of galaxies and clusters, the universe's baby picture, with a mottling of warm and cool spots encoding the initial blueprint of cosmic structure. So at 380,000 years old, the universe has become a relatively cool 3000 K neutral hydrogen and helium gas, filling space almost uniformly, and it's transparent. The brilliant youthful glow has now faded into a dull red warmth, and then beyond visible light entirely. What followed is a period often poetically called the Cosmic Dark Ages. Why dark? Because now, with the primordial glow gone, there were as yet no stars or galaxies shining. The universe was transparent and dark. The gas was cooling. The light from the Big Bang was drifting outward and redshifting into invisibility, and space was largely unilluminated, save perhaps for very faint glows from atomic transitions or cooling gas. Nothing like the bright lights of stars. An observer floating at, say, 100 million years after the Big Bang would see a black sky. The temperature of the background radiation would be a few tens of Kelvin, so mostly microwave radio waves, nothing to see with eyes. Yet all around, gravity was quietly working on the slightly denser patches of gas, drawing them inwards. Gas was not perfectly uniform throughout the universe. Those cooler, slightly denser regions of the primordial gas, the ones corresponding to slightly cooler spots in the CMB, exerted a bit more gravitational pull. They began to gather more gas from their surroundings. Invisible clumps of dark matter, more on this mysterious component soon, were also drawing gas into their deep potential wells. During these dark ages, the universe was like a calm night where nothing visible happens, but seeds are germinating under the soil. Gravity amplified the tiny variations, slowly but surely, pulling hydrogen and helium into ever-growing clouds and filaments. The distribution of matter started to resemble a spider web, dense nodes connected by filaments, with voids in between, though at this early time it was all still diffuse and no stars had lit up. After perhaps a few tens of millions of years, the largest of these gas clouds, particularly where the invisible dark matter had clustered strongly, grew dense enough at their cores to trigger a new phenomenon. The gas at the center of such a cloud, pulled in by gravity, began to heat up as it fell inward. Kinetic energy, of infall converted to thermal energy. Eventually, one critical cloud crossed a threshold. Its core reached temperatures of millions of degrees and high pressure. Nuclear fusion ignited. A huge burst of energy was released from the core, and a delicate balance was struck between gravity and pressure. A star was born, the first star in the universe. In pockets across the cosmos, this process repeated. Wherever a pocket of gas became dense and hot enough, a new star lit up. The first stars were likely very massive, dozens or hundreds of times the mass of our Sun, because without heavier elements, like carbon or oxygen in the gas, it couldn't cool as efficiently, and thus fragments of collapsing gas clouds tended to be large. These first stars burned a bright blue-white, extraordinarily luminous, and very short-lived by stellar standards. One by one, like brilliant blue-white beacons, they pierced the cosmic dark. It was as if the universe saw the light of its first campfires, kindling in a vast, cold wilderness, points of illumination sparking up in the blackness. The era of reionization had begun. Each first star flooded its neighborhood with energetic ultraviolet photons. These photons had the power to ionize neutral hydrogen, that is, to knock electrons off atoms. The neutral gas around each new star became electrically charged, ionized, once again, forming bubbles of plasma amidst the neutral background. Initially, these ionized bubbles were small, centered on individual stars or star clusters. But massive stars live briefly. In a few million years, many of them would have died in violent supernova explosions, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. New stars were born in those same regions, some a bit smaller and longer-lived, thanks to the cooling effect of the newly introduced heavy elements. Over several hundred million years, more and more stars formed, and the ionized bubbles around clusters of stars grew and merged. As the first generation of stars grouped into the first proto-galaxies, their combined ultraviolet glow carved out ever-expanding cavities of ionized gas. Imagine the once neutral universe now being Swiss cheesed by growing holes of ionization. Finally, by around 1 billion years after the Big Bang, nearly all the remaining hydrogen in intergalactic space was ionized again. The universe became transparent to ultraviolet light as well, as the last fog of neutral hydrogen was banished from intergalactic space. The Dark Ages had fully ended. The universe was filled with starlight. During this epoch, the cosmic landscape transformed rapidly. Gravity pulled the early star clusters into tighter groups. These groups merged to form nascent galaxies. The first galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They often were chaotic assemblages of stars, blazing with the light of massive new stars and the explosions of supernovae. Over time, small proto-galaxies merged to form larger ones. The cosmic web, the large-scale structure of matter, became more pronounced. Filaments of dark matter and gas channeled material into the growing galaxies, while vast voids were emptied of matter as it flowed towards the filaments. Some of the early massive stars likely collapsed into black holes after they died. These could have become seeds for the supermassive black holes we find in galaxy centers today. Indeed, by as early as 700 million years after the Big Bang, we have evidence from quasars observed by telescopes that some black holes of billion solar mass scale had already formed and were devouring matter, shining as intensely luminous quasars. That indicates the assembly of galaxies and black holes was well underway very early. In those first billion years, the universe went from a dark, uniform fog to a web of glowing galaxies. It was a dramatic transformation, a kind of cosmic adolescence full of growth spurts and turbulence. Over the next several billion years, this web of structure became ever more complex and beautiful. Gravity and time together sculpted an immense cosmic architecture. Galaxies gathered into groups and clusters. and those clusters themselves drew together into larger complexes called superclusters. On the grandest scales, matter arranged itself in filaments and sheets, weaving around enormous voids. This pattern is the cosmic web. The web forms as the gravitational attraction of matter draws things together along the path of slight initial overdensities. Galaxies are not scattered randomly. They lie along these filaments. Where filaments intersect, we get clusters and superclusters of galaxies, immense nodes of the web. In between lie voids, vast regions with far fewer galaxies, as if the web's threads outline bubbles of nearly empty space. To visualize the cosmic web, imagine looking at a frothy foam or a network of neurons in a brain. Clusters and superclusters are like the knots, filaments like the threads between, and voids like the empty gaps. One filament can stretch hundreds of millions of light years from end to end. Observations have revealed structures such as the Sloan Great Wall and others that span over 1 billion light years. Chains of galaxy clusters lining up. The largest structures known, great walls of galaxies, huge quasar groupings, approach scales where the word structure itself starts to blur, because on scales above a few billion light years, the universe looks homogeneous. Still, these enormous formations amaze us. For instance, one huge grouping of galaxies called the Bootes supervoid, though it's a void, is so large and empty that if galaxies were peas scattered across space, it would be like an expanse, tens of millions of kilometers with only a handful of peas. It's a tremendous volume of space, with hardly any galaxies at all, akin to a great cosmic cavern. Within the filaments, galaxies continue to interact. Galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity, form at filament intersections. Our own galaxy, the Milky Way, is part of a small cluster, or group, called the local group, which in turn sits on the outskirts of the Virgo supercluster, which itself is part of an even larger structure, often called Laniakea, a supercluster complex spanning 500 million light-years. Our local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Laniakea, a Hawaiian word meaning immeasurable heaven, includes the Virgo cluster and hundreds of other groups, all flowing within a common gravitational basin. It is just one of many superclusters in the observable universe. Even within our local group, cosmic evolution continues. The Milky Way and the Andromeda galaxy are drifting inexorably toward each other. In about 4 billion years, they will merge, forming a new, larger galaxy. This will be a slow-motion collision. Stars are so far apart that few, if any, stars will hit head-on. But the two galactic disks will distort and blend, likely forming a big, elliptical galaxy with a new structure. Such mergers have happened countless times in cosmic history, especially in clusters where galaxies are crowded. It's one way galaxies grow and transform. Our own eventual merger is just a small chapter in the long story of structure formation, but it highlights that even galaxies themselves are impermanent, ever-changing. The cosmic web forms a sort of scaffolding that cradles everything that exists within the universe. And remarkably, the shiny galaxies we see, the gas, dust, and stars, are only a small fraction of the matter involved in this structure. There is an invisible component called dark matter that outweighs the ordinary matter by about 5 to 1. Dark matter neither emits nor absorbs light, so we don't see it directly, but its gravity betrays its presence. It was dark matter that seeded the cosmic web. During the Dark Ages, dark matter clumped under gravity. It does not interact via light or pressure, so it started collapsing even when normal matter was still a hot plasma. These dark matter clumps served as gravitational wells, pulling in ordinary gas after it became neutral. Without dark matter, the gas alone might have taken much longer to form stars and galaxies, but with it, structure formation was boosted. Every galaxy sits in a cushion of dark matter, a dark halo, much more massive and extended than the galaxy's visible extent. In clusters of galaxies, The combined dark matter of the cluster creates deep potential wells that hold the cluster together. In fact, observations of galaxy clusters in the 20th century first provided evidence of dark matter. Galaxies were moving too fast to be held by visible matter alone. So one can picture the cosmic web as an invisible framework of dark matter, upon which gas settled and cooled to produce galaxies. The luminous matter traces the patterns drawn by dark matter's gravity. By around 5 billion years after the Big Bang, many of the structures we see today were in place. The cosmic web was well established. Galaxies had matured and grouped into clusters and superclusters. Stars had been forming for billions of years in those galaxies. In fact, the peak of star formation in the universe likely occurred around 3 to 4 billion years after the Big Bang, when galaxies were in a star-bursting frenzy. After that peak, star formation gradually declined as the gas reservoirs in galaxies were used up or heated or expelled by various processes. In fact, around this midpoint in cosmic history, the conditions were ripe for planetary systems like our own to form. Generations of earlier stars had enriched the interstellar gas with heavy elements, carbon, iron, oxygen, etc., forged in stars and supernovae. In one typical spiral galaxy, our Milky Way, a cloud of such enriched gas and dust collapsed around 4.6 billion years ago to form a new star, our Sun, and a retinue of planets. This was possible because at least 9 billion years had passed since the Big Bang, allowing multiple cycles of star birth and death to scatter the ingredients for planets. Our Sun lit up in a relatively quiet corner of the Milky Way, and around it formed a system of planets, including Earth. On that young Earth, formed from cosmic dust and the debris of earlier stars, complex chemistry began to brew in its oceans and atmosphere. By a few 100 million years after Earth's formation, life arose, simple at first. Over eons, that life became more complex, leading to creatures that could look up and marvel at the stars. In this way, we humans are very much a product of cosmic evolution. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in long-dead stars and scattered through space, incorporated into the Sun and Earth, and ultimately into us. Our emergence is an exquisite example of the universe giving rise to organized complexity capable of contemplating itself. While this was happening on the scale of galaxies and life, another, even larger scale drama was unfolding in the background: the expansion of the universe itself. Since the Big Bang, the universe has been expanding, but for a long time, it was expected that this expansion should be slowing down due to the pull of gravity. Indeed, for the first few billion years after the Big Bang, the expansion was decelerating. The mutual gravity of all the matter in the cosmos was putting the brakes on the expansion. Galaxies, though being carried apart, were doing so at an ever-slowing rate. One might have imagined that given enough time, the expansion might even stop and reverse if gravity was strong enough. However, about 6 or 7 billion years after the Big Bang, roughly at the time our Sun formed, something curious started to happen. The expansion began to speed up again. Galaxies started to recede from each other faster and faster. This discovery, made by observing distant exploding stars, supernovae, in the late 20th century, was revolutionary. It implied the presence of a new ingredient in the cosmic recipe, something pushing the universe outward. We call this mysterious influence dark energy. Dark energy is the name we give to the unknown cause of the accelerated expansion. It appears to act much like what Einstein once hypothesized as a cosmological constant, an intrinsic energy of empty space. Einstein originally introduced such a term to allow for a static universe, then removed it when expansion was discovered, reportedly calling it his biggest blunder, not realizing the universe actually does have a similar effect present. Dark energy doesn't dilute as the universe expands. It remains, as far as we can tell, constant in density. As space grows, the total amount of this energy increases, because more volume times the constant density yields more energy. In effect, dark energy is like an anti-gravity pressure uniformly filling space, pushing things apart. For the first several billion years, dark energy was negligible compared to matter. Matter's gravity was slowing the expansion. But as matter spread out and its density dropped, dark energy eventually became significant. About 5 billion years ago, dark energy's repulsive effect overtook the self-gravity of matter in the universe. The expansion, which had been slowing, stopped decelerating and began to accelerate. Small distances, like within galaxies or clusters, weren't affected. Those structures are bound by much stronger local gravity. But on large scales, between clusters and superclusters, the gaps began to widen faster and faster. To picture the effect of dark energy, imagine the universe's expansion as a ball that was thrown upward, the Big Bang being the throw. First, the ball climbs, but slows, gravity's pull. Then, unexpectedly, it starts accelerating upward as if pulled by an unseen force. Dark energy is akin to that unseen force, accelerating the expansion of the cosmic ball. Another analogy. Think of 2 points in space with a spring between them, gravity, and an expanding rubber sheet under them, space itself expanding. Initially, the spring slows their separation, but if the rubber sheet stretching, dark energy, grows strong enough, it will overcome the spring and the points will fly apart faster and faster. The simplest form of dark energy, consistent with observations, is a true cosmological constant, an unchanging energy woven into the fabric of space-time. If that is the case, then the fate of the universe is a continual acceleration. Distant galaxies will recede at ever-increasing speeds. Eventually, far in the future, distant galaxies currently visible will be carried beyond our horizon of visibility because space is expanding so fast that light from them can no longer reach us. The night sky over tens of billions of years will grow emptier as galaxies vanish from view one by one. Today, dark energy makes up about 68% of the total energy content of the universe. Matter is about 32%, of which about 27% is dark matter and 5% normal matter. Thus, the cosmos, by composition, is mostly this invisible, dark energy. It's astonishing. All the galaxies, stars, gas, and dust, everything we see, is only a trace component. Yet, it is thanks to that small component that we have structure and life. Dark energy, ironically, mostly influences the voids and the eventual destiny. Even now, dark energy's presence is subtle on human timescales. The Milky Way and Andromeda will still collide despite cosmic expansion because they are gravitationally bound strongly enough to overcome expansion at local scales. The local group of galaxies will remain together, but clusters that are not bound to us will drift away. For instance, galaxies in the Virgo cluster, tens of millions of light years away, will recede further. In a few 100 billion years, should any observers be around, virtually all galaxies beyond the local group will have disappeared from view, being carried away faster than light can catch up. To summarize the cosmic inventory and its effect, dark matter provided the scaffold for structure and still holds galaxies and clusters together. Dark energy drives the overall expansion ever faster. Normal matter, atoms, forms the stars, planets, and living beings. Each plays a role in the grand cosmic story. Dark matter pulled the cosmos into a beautiful web. Normal matter lit that web with stars. Dark energy is now pulling the web apart at its largest scales. Time marches forward, and with it comes change. But why does time have a direction at all? We recall the early universe was an extremely hot, uniform state, and now we have a clumpy cosmos and cool expanses. Things have clearly moved from a state of order to increasing disorder. This one-way progress is encapsulated in the concept of entropy. The second law of thermodynamics says entropy, disorder, tends to increase in a closed system. This law underpins the arrow of time. Eggs break, but do not unbreak. Cream disperses in coffee, but never spontaneously gathers back at the top. A piece of paper burns to ash and smoke, but the ash and smoke won't reconstitute into paper on their own. These processes involve increasing entropy, and they define an irreversible direction to time, from past, lower entropy, to future, higher entropy. The universe as a whole began in a state of incredibly low entropy. At the moment after the Big Bang's initial inflationary smoothing, matter and radiation were almost perfectly uniformly spread. Paradoxically, uniform gas is a low entropy state in cosmology because gravity can do a lot of work with it. Imagine a smooth spread of matter that can clump versus matter already clumped into black holes. The latter is a higher entropy state gravitationally. The early universe had very low gravitational entropy, everything spread out smoothly, and not maximal thermodynamic entropy either. There were temperature differences and lots of free energy available. This special beginning, perhaps set by inflation or whatever preceded it, is why there was an arrow of time. The cosmos started wound up, like a clock with a lot of free energy and potential to evolve into more disordered states. As the universe aged, entropy increased. The formation of stars and galaxies might seem like an increase in order locally, but overall, entropy rose because, for example, when a star shines, it produces a lot of thermal radiation, high entropy, out of nuclear fuel, lower entropy state. The light that escapes into space carries away entropy. The net effect of all processes, gravitational clustering, star formation, life, has been to increase total entropy. Entropy is now vastly higher than in the pristine early universe, and it will continue to increase. What is the ultimate fate implied by ever-increasing entropy? It is often called the heat death or big freeze. This scenario is a universe where, on the largest scales, everything becomes uniform again. Not in a low entropy way like the beginning, but in a maximum entropy way. A thin mist of particles and radiation at near uniform temperature, with no gradients to power any process. If dark energy continues to accelerate expansion forever and nothing intervenes, this is the likely end state, trillions upon trillions of years hence. Let's trace that future vision. First, over the next few trillion years, star formation in galaxies will taper off. Galaxies have a finite supply of gas to make new stars. Eventually, that gas runs out or becomes locked in stellar remnants. The longest-lived stars, small red dwarf stars, can burn for trillions of years, far longer than the current age of the universe. So, billions of years from now, galaxies will be dominated by long-lived red stars slowly fusing hydrogen. As time marches on, even these will exhaust their fuel. By around 100 trillion years from now, 10-14 years, the era of star formation will officially end. We enter the so-called degenerate era, dominated by stellar remnants. In that far future, the galaxies, those that remain gravitationally bound, like our future Milkdromeda, the merged Milky Way Andromeda, will be populated only by degenerate objects, white dwarfs, cores of spent stars, neutron stars, brown dwarfs, failed stars, and black holes. New stars will no longer be born. The remaining stars will slowly cool and dim. White dwarfs, starting hot, will radiate their energy over billions and trillions of years, turning into black dwarfs, cold, dark, stellar embers. Planets, if any still orbit, will gradually spiral into their stars or be flung out by gravitational encounters over extremely long timescales. At this point, entropy is still increasing. Complex structures decay. Perhaps some hypothetical, incredibly long-lived civilization might find ways to survive around fading sources of energy, but eventually usable energy supplies would dwindle. After many trillions more years, even larger structures start to destabilize. Gravitational interactions within what's left of galaxies will gradually eject many objects into intergalactic space, a process called dynamical relaxation. Central black holes might collect some matter, while other stars or remnants are thrown to the outskirts or beyond. Fast forward to unimaginably distant times. 1019, 1020, up to 1040 years. By 1020 years, most galaxies as we know them may disperse, stars either fallen into central black holes or scattered. Around 1040 years, a number so large it defies comprehension, even protons, if unstable, some particle theories suggest protons might eventually decay, will have decayed into lighter subatomic particles. If proton decay is real, at this point, solid matter dissolves. Planets, white dwarfs, any remaining asteroids or dust, all would literally evaporate into radiation and elementary particles. The universe becomes a dilute soup of electrons, positrons, neutrinos, and photons, perhaps with some lingering protons if they're absolutely stable, and lots of dark matter particles. Assuming dark matter is stable and doesn't decay, we aren't sure, but likely it is stable. One might think black holes would still be around as massive reservoirs of mass, even after normal matter is gone. And they will, for a long time. But even black holes aren't eternal. Stephen Hawking theorized that black holes slowly evaporate by emitting Hawking radiation, a very slow quantum thermal glow that causes them to lose mass over time. For stellar mass black holes, the evaporation time is around 10^67 to 10 years. For supermassive black holes, millions or billions of solar masses, like in galaxy centers, the time is stupendously larger, on the order of 10^98 to 10^100 years or more. But given enough time, even these giants will eventually evaporate completely, each ending in an explosive burst of high-energy particles when its mass becomes very small. After the last black hole has vanished, the universe enters its final stretch, the dark era. The temperature everywhere will approach an extremely low value as expansion dilutes any remaining energy. Essentially, what remains is a sparse sea of photons, mostly of extremely long wavelength radio waves, some electrons, positrons, neutrinos, and perhaps some dark matter particles if they haven't decayed, all spread so thin that in a volume the size of our Earth, you might find essentially none of those particles. Entropy is maximized. In a sense, the cosmos returns to a featureless state, not of super-hot plasma like the beginning, but of near-empty cold space. All gradients of temperature or density are ironed out. With no free energy differences, no work can be extracted to power any process. Change virtually halts. This is the heat death. Time would still pass, but nothing of significance would mark its passage. It's a ghost universe, silent, empty, and everlasting, unless some fluctuation eventually breaks the stalemate, which we'll touch on. The arrow of time at that point would effectively cease to matter, because there would be no events to distinguish past from future. The great cosmic drama would have quietly exited stage right. However, this fate assumes a constant dark energy and no new physics intervening. We must acknowledge other possibilities. The universe's end might be more dramatic or lead to a rebirth. One such possibility is the Big Rip scenario. If dark energy is not constant, but instead grows in strength, for example, its equation of state has W1, a so-called phantom energy, the acceleration would become more and more violent. Eventually, even gravitationally bound systems would not hold together. In a Big Rip, first clusters of galaxies would be torn apart, galaxies receding from each other despite being bound, effectively overcoming their mutual gravity. Next, galaxies themselves would be shredded, stars flung out as the space within the galaxy expands faster than the galaxy's gravity can keep up. Closer to the rip, solar systems would unbind, planets would fly off from stars. In the final moments, stars and planets would be ripped apart, and even atoms and atomic nuclei would be sundered in the ultimate blow. The timeline for such an event depends on how phantom the dark energy is. If it were just slightly more negative than 1 in its equation of state, the Big Rip might be trillions of years away, or not happen at all, if it tends asymptotically to a constant. If it's substantially more negative, The rip could happen sooner, though current data suggests dark energy is very close to a cosmological constant, World 1. The concept is spine-chilling, the fabric of space accelerating so wildly that it rips apart anything bound. Matter is literally disassembled by the expansion of space. Most physicists consider this unlikely based on current evidence, but it's not ruled out absolutely. If our current best fit is slightly off, the cosmos might end not in ice, but in a singular crescendo of tearing apart everything. Another scenario, the Big Crunch. This is in a sense the opposite of heat death or Big Rip. It's a reversal of the expansion into a contraction. If, for some reason, dark energy were to dissipate or turn attractive, and if the density of matter were high enough, gravity would eventually win out and pull everything back together. The expansion would slow, stop, and reverse. Distant galaxies would start to approach rather than recede. Over billions of years, what was once an expanding universe becomes a collapsing universe. Galaxies would rush together. Clusters merge into a supercluster, superclusters into huge sheets, and finally all material closes in. The temperature of the background radiation, which had been dropping for eons, now starts to rise again as space compresses that radiation. The dark, quiet cosmos would light up once more as every particle of light gains energy and blue shifts. Galaxies might careen into each other with increasing frequency. The night sky would glow brighter and brighter as more galaxies cram into our observable view, and the heating of all gas triggers star formation, or makes existing stars shine more fiercely. In the far future of a Big Crunch, the universe's scale continues to shrink. What were galaxy superclusters a few billion years before are now overlapping and colliding. Eventually, all matter might coalesce into an extremely dense state. The temperature would soar to star-like or greater levels everywhere, ionizing whatever atoms existed once more. Fusion could ignite in giant bursts as gas clouds compress. Essentially, the reverse of the universe's expansion timeline happens. Clusters of galaxies collapse into blazing quasars, then into massive nebulae, then into a shrinking ball of plasma, then perhaps into conditions similar to the very early universe. If quantum gravity or other effects don't intervene, this collapse could lead all the way back to a state of seemingly infinite density and temperature. Essentially, a mirror image of the Big Bang, sometimes dubbed the Big Crunch. Is that truly an end, or could it be a bounce? Some modern theories speculate that a Big Crunch could transition into another Big Bang, the death of one universe seeding the birth of a new one. In cyclic models, the universe might undergo endless, or at least many, Bang Crunch cycles. Ancient cosmologies, like Hindu cosmology, imagined time as cyclical, cosmic days and nights of Brahma, with universes expanding and contracting periodically. A scientific version might be, after a crunch, all space and time re-expand again, maybe after reaching a singularity, or perhaps never fully reaching infinite density because new physics causes a rebound. If there is a bounce, the astonishing implication is that our Big Bang might not have been the absolute beginning, but simply the latest bounce. Some theorists working in quantum cosmology and string theory have explored models where, for example, our 3D universe, brain, periodically collides with another brain, causing big bangs in a cycle. Others, loop quantum cosmology, find that quantum effects could cause space to repel at extremely high densities, avoiding a singularity and starting expansion anew. If the universe can bounce, what happens to entropy and the arrow of time in such a cycle? That's a tough question. Naively, entropy would carry over and increase with each cycle, which would be problematic. You can't cycle indefinitely if entropy irreversibly accumulates, unless the bounce somehow resets the entropy or disposes of it. Some proposals, like conformal cyclic cosmology, Roger Penrose's idea, suggest that at the end of a heat-death scenario, when the universe is nothing but photons and essentially devoid of scales, it might be possible to relabel that state as the initial singularity of a new Big Bang. Since a universe of only structureless photons has no concept of time or size, It could be equivalently reinterpreted as a new Big Bang state. This is speculative and not widely accepted yet, but it shows how creative thinking is being applied to the idea of cosmic rebirth. There are also other theoretical fates. One is a vacuum decay scenario. Perhaps our current vacuum, the ground state of fields in the universe, is not the true lowest energy state. If there exists an even lower state, the universe could at some point quantum tunnel into that lower state. If that happened, a bubble of true vacuum would appear somewhere and then expand at near the speed of light, converting everything it touches into a new state of being. Within that bubble, the laws of physics might be different constants, particle arrangements. So essentially, it's like a new universe erasing the old one. This bubble nucleation and expansion would be catastrophic, from our perspective, and extremely fast. One moment everything's fine, the next, a bubble of alien vacuum is rushing through you, disintegrating you, Earth, and every structure, and we'd never see it coming because it expands at light speed. It's a wild idea, but certain particle physics models make it a possibility. For instance, if the Higgs field sits in a metastable false vacuum. Current data suggests it's not highly likely in the near term. If it can happen, it might be trillions of years away or more. Or maybe it's truly stable and won't happen at all. In any case, it's another way nothing, or rather a different something, could be born from our something, effectively resetting the cosmic stage abruptly. Finally, even in the heat-death scenario, some have mused about the possibility of random fluctuations creating new ordered patches. Given infinite time in a static de Sitter universe, the end state with dark energy domination, quantum fluctuations could occasionally, by sheer chance, produce a small region of lower entropy, perhaps even a new Big Bang seed, or a so-called Boltzmann brain, a spontaneously formed self-aware entity out of chaos. While these ideas are thought experiments and lead to some absurd-sounding consequences that physicists debate, often to argue that an eternal de Sitter phase might be problematic or that some new physics must intervene before infinity, they speak to the richness of considerations about eternity. Even in an endless nothingness, given unlimited time, perhaps a fluctuation might trigger a new creation event. The probability is incredibly low for any given moment, but in infinite time, the unlikely becomes inevitable. So perhaps heat death isn't truly the end. It could be a plateau before another beginning, in an endlessly cyclic multiverse of fluctuations. This is deeply speculative, verging on philosophical, but it shows that even finality might not be absolute. At this juncture, we've painted possible endings, eternal expansion into heat death, a big rip, a big crunch with possible bounce, or a transition to something entirely different. Each path carries different implications for the arrow of time and for the question of whether the universe has a purpose or just a lifespan like any other natural phenomenon. From what we can tell now, with our cosmological measurements, the most likely fate is an ever-accelerating expansion leading to a very cold, very empty universe. Heat, death. But our knowledge is incomplete. Dark energy could surprise us by changing behavior. New physics, like interactions between dark energy and matter, or a slow dilution of dark energy, could alter the story. Now, let's step beyond even these questions of our universe's fate and ask, is our universe the only universe? For much of our narrative, we presumed that the universe meant all that exists. But modern physics has opened the door to the idea of a multiverse, a larger reality in which our universe is just one part. There are actually different notions of multiverse that scientists discuss. One arises from quantum theory, the many worlds. Interpretation suggests that all possible outcomes of quantum events actually occur, each in its own separate branch of reality. In that view, reality continually splits into a vast ensemble of parallel timelines. That's a kind of multiverse, a branching tree of universes coexisting in superspace. It's a very different concept from universes separated by space. It's more like parallel dimensions or alternate histories. It might not affect our cosmic story directly, so let's set that aside after noting it as an intriguing possibility. Parallel universes where, say, different events happened in history, etc., playing out side by side unbeknownst to each other. The multiverse idea, more relevant to cosmology, arises from cosmic inflation and string theory. If inflation occurred as our theories suggest, the ultra-fast expansion in the universe's infancy might not have been a one-time event that ended everywhere at once. There are strong reasons to suspect inflation is eternal. While it ended in our region, allowing our Big Bang fireball to proceed, in other far-flung regions, inflation might still be going on, endlessly creating more bubble universes. Picture a vast, inflating space-time, a kind of ever-growing foam. Occasionally, in that foam, regions stop inflating and crystallize into hot Big Bang bubbles like ours. Each bubble is a universe in its own right, with potentially different properties depending on slight quantum variations when inflation ended there. Our observable universe would be just one bubble that happened to nucleate 13.8 billion years ago. There could be countless others. These other universes are not located in our space. They are separated by continuing inflating space, which expands so fast that we can never catch up to the neighboring bubbles. They are forever out of reach. Each bubble might have different physical constants, particle content, even dimensionality, especially when combined with ideas from string theory. String theory suggests that the vacuum of the universe, the configuration of extra dimensions and fields, could have many possible states, sometimes quoted as 10 to 500 or more possibilities in the landscape of string theory solutions. Each bubble universe could realize one of those many possibilities. That offers a tempting explanation for why our universe has the peculiar laws it does. If there is a multiverse of all kinds of universes, we just happen to be in one that had the right conditions for galaxies, stars, and life, because otherwise we wouldn't be here to observe it. This is a kind of anthropic selection from a multiverse ensemble. It's important to note, none of this multiverse speculation is confirmed, but it is grounded in serious physics theories. Eternal inflation is a rigorous outcome of many inflation models. Once inflation starts, it generically doesn't stop everywhere, so while one bubble forms, inflation continues elsewhere, leading to potentially infinitely many bubble universes. And in string theory, the many possible shapes of extra dimensions, each giving rise to different physical constants, combined with inflation, virtually guarantees a multiverse. The inflating space fills itself with regions realizing all those options. Can we detect or observe evidence of other universes? It's challenging by definition. If they are truly separate, we can't see into them. But one possible sign would be if a neighboring bubble universe in the early inflationary period happened to collide with our bubble. That collision might leave an imprint, perhaps a circular pattern or a particular kind of distortion in the cosmic microwave background. People have actually searched CMB maps for hints of such collisions. So far, none have been convincingly found, but the search exemplifies how we don't shy away from trying to test even outrageous-sounding ideas. Another hint could come from the distribution of gravitational waves or subtle effects on the distribution of galaxies, none detected yet in a way that screams other universe. Another multiverse notion comes from higher dimensions and brane world scenarios. String theory requires extra spatial dimensions, 6 or 7 beyond our usual 3. Those dimensions could be compactified, curled up small, or in some models, we could be confined to a 3D brane floating in a higher dimensional space. There could be other branes, essentially other universes, separated from ours in the extra dimensions. Normally, we'd have no interaction with them except perhaps gravity, which can propagate in the higher dimensional bulk. Some have even imagined that a collision between branes could be what the Big Bang was. 2 3D worlds collided, releasing energy that flooded our brain with the hot matter of a Big Bang. If those other branes, universes, exist, They are right next door, in a sense, perhaps only a tiny distance away in a fourth spatial dimension. But we can't see them or touch them because our particles and light are confined to our own brain. It's a mind-bending concept. Other entire universes, potentially a millimeter away from us, in a direction we can't perceive. Whether it's bubble universes, parallel quantum worlds, or higher dimensional brain worlds, the multiverse idea profoundly changes the context of our cosmic story. Our universe could be a small chapter in an infinitely larger ensemble. It could mean that what we consider the ultimate beginning, the Big Bang, is just one local event in an eternally evolving multiverse. And it forces interesting questions. If there are countless universes, each with possibly different physics, what does that say about meaning? One could imagine each universe as having its own narrative, its own potential for life, or even intelligence. Are there other conscious beings out there, not just in our universe, perhaps in distant galaxies, but in entirely separate universes, forever causally disconnected from us? This drifts from science into philosophical wonder, because by construction, we may never verify those other universes. Yet, the theories that predict them, inflation, quantum mechanics, string theory, are in principle testable in other ways and have earned credibility. So we take the multiverse seriously, while acknowledging it currently lies at the speculative frontier. Regardless of whether there's a multiverse, we find ourselves in this universe, with its particular story. From a singular beginning, or at least an extremely hot, dense early state, our universe expanded, cooled, formed structures, and eventually produced us, beings capable of reflecting on the whole process. We've gone from contemplating mythic cosmologies to actually measuring the geometry and expansion history of the cosmos. We discovered the universe had a beginning, Big Bang, that it is 13.8 billion years old, that it expands, that it has a cosmic web of structure, and that it is dominated by dark matter and dark energy. These are incredible revelations, won through the hard work of observation and theory, building on generations of curious minds. Now we turn to the philosophical and existential implications of the cosmic story. Standing under the night sky, we can feel two seemingly opposite emotions: insignificance and profound connection. On one hand, the universe is vast beyond imagination. The Earth is a tiny pebble in a gigantic space. Even our galaxy, with 100 billion stars, is just one in a sea of billions of galaxies. Physically, we occupy no privileged position. The cosmos is not arrayed with humanity at the center. We are off in a corner of an average galaxy, which itself is in a supercluster that is unexceptional among others. Time-wise, human history is an eye blink compared to cosmic time. The stars shone for billions of years before we came along. They will continue billions of years after we are gone. It's humbling, even daunting, to recognize this. The famous pale blue dot photograph taken by Voyager 1 from beyond Pluto, showing Earth as a tiny bluish speck in the void, encapsulates that humility. All of human history, every joy and sorrow, every hero and villain, played out on that mote of dust, suspended in a sunbeam in the vast darkness. When confronted with such scale, it's natural to feel small. Yet, on the other hand, how marvelous that we can comprehend this scale. We are made of particles that were forged in stars. Essentially, the universe gave birth to conscious organisms that can observe and contemplate the universe. We are a way for the cosmos to know itself, a sentiment popularized by Carl Sagan and profoundly true. Our atoms originated in the Big Bang, hydrogen, or in stellar furnaces, carbon, oxygen, nitrogen, etc., or in supernovae, iron, zinc, iodine, gold, all the heavier elements. We are literally children of the stars, made of stardust. Through us, the materials of the universe have become aware and curious. That imbues us, and possibly other intelligent life out there, if it exists. with a kind of cosmic significance, albeit a self-bestowed one. We carry the legacy of 13.8 billion years of cosmic evolution in our bodies. When we gaze out at the galaxies, those galaxies are in a sense observing themselves through our eyes. The emptiness of space, while vast, is not completely empty. It's filled with fields and particles and possibilities. Likewise, the perceived emptiness or pointlessness one might feel when confronted with a giant, cold universe can be filled with our own meaning and purpose. The cosmos doesn't hand us a script. Instead, it gives us the stage, the raw materials, and the invitation to create meaning. And humans have been doing that for as long as we have existed, through story, science, art, love, and exploration. We find that the more we learn about the universe, the more beautiful it becomes. Consider the fact that the atoms in your body were once inside of a star, perhaps many different stars over the eons. In a very real sense, you are as old as the universe, because the matter that composes you has been around since the beginning, apart from some recent transmutations via nuclear reactions. We are deeply connected to the cosmos. Every breath you take contains atoms from all over Earth and beyond, even some noble gas atoms that were forged in the Big Bang. The water you drink contains hydrogen made at the dawn of time. The calcium in your bones was fused in some star that ended its life long before Earth formed. We are a microcosm of the universe. This perspective can evoke a sense of spiritual awe, even in a non-religious framework. It's the awe of existence itself, the recognition that we are part of something vast and magnificent. The American astronomer Harlow Shapley said, "We are akin to the totality of things. The atoms don't belong to us, we belong to them. We are a moment in their journey." The universe's story also imparts lessons. One is the transient nature of all things. Stars are born and die. Even galaxies collide and merge. The universe evolves. Change is the rule. On Earth, we see that civilizations rise and fall, species come and go, all part of that cosmic change. But amidst change, there is continuity. The continuity of matter and energy, and the continuity of information passed on. Our sun inherited matter from previous stars. We inherited molecules from Earth's past life. We pass our atoms back to the Earth when we die. It's a kind of immortality, not personal immortality, but the persistence of our substance and our influence. A star that died billions of years ago in our region of the galaxy, by dying, it seeded the cloud that formed our solar system. In a way, that star lives on through us. Likewise, the choices we make and the knowledge we gain might propagate far into the future, indirectly shaping things we will never see. When we build a telescope and discover something, that knowledge changes the consciousness of humanity, which may alter our future actions and fate. Our cosmic understanding has also, interestingly, circled back to some ancient wisdom. Many cultures intuited a connectedness of all things, or a cycle of creation. The scientific specifics we've learned differ from the myths. The universe isn't literally the egg of a giant bird, for instance, but the emotional thrust that we are part of a greater whole is affirmed more strongly than ever by science. We now see that the same physical laws apply everywhere. We've sent probes to other planets and found familiar chemical processes at work. We've detected light from atoms in distant galaxies and found the same spectral lines as atoms we study in labs. The universe has a unity, and the story of cosmic evolution is a single, continuous narrative from the Big Bang to the present and onward to possible futures. We are a chapter in that narrative. In contemplating the end scenarios like heat death or Big Rip, one can feel despair. Will it all amount to nothing? But one might also find liberation in it. The distant future is beyond our control. What matters is what we do with the time and universe we have. The fact that the universe will end in one way or another does not negate the preciousness of its present. In fact, it enhances it. Just as mortal beings find meaning in life partly because it is finite, The finite window of a lively universe can galvanize us to appreciate its wonders all the more. We live in a cosmic springtime, when conditions are just right for complexity and life. It will not always be so, but how fortunate that it is so now, and that we are here to witness it. There's also a school of thought that even if our universe fades, perhaps life, or an advanced form of intelligence, could in some way continue or influence beyond its own universe. Some speculative ideas suggest extremely advanced beings might even hop between universes or create baby universes artificially. These ideas blur science and philosophy and remain in the realm of imagination for now. But the mere consideration expands our sense of possibility. Perhaps the end of the universe isn't an absolute wall, but just another frontier to transcend for a sufficiently ingenious civilization. It sounds like science fiction, and it certainly is right now, but who can definitively say what a Type 3 or Type 4 civilization, if it could exist, might achieve after millions or billions of years of evolution? Bringing our thoughts back to the here and now, the night sky. It connects us to all of this grand history and future. When you next stand under the stars on a clear night, think about the journey of a photon that enters your eye. Perhaps it left a distant galaxy when that galaxy was young and our planet not yet formed, traveling across expanding space for tens of millions of years, through voids and past clusters, until finally, one night, it ended its journey on your retina, triggering a chemical reaction that led to an image in your brain. In that moment, you, a being of stardust, assembled on an 8-planet minor system around an unremarkable star, catch a whisper from the other side of the universe. And with collective effort, humanity has learned to interpret these whispers, to tell a coherent story of how we came to be. The cosmos is mysterious and beautiful. Every discovery seems to open new questions. We determined the age and shape of the universe, only to find most of its content is invisible, dark matter and dark energy. We may solve dark matter, perhaps a type of particle, and dark energy might remain puzzling or turn out to be a property of space itself. We look for potentially habitable exoplanets, wondering if life arose elsewhere. We tune our radios for possible signals from other civilizations, not knowing if we are alone or one of many. We delve into the quantum foam, attempting to reconcile general relativity, our theory of the very large, with quantum mechanics, the theory of the very small, hoping for a deeper understanding that might unify forces or reveal why the Big Bang happened the way it did. The quest goes on. Through it all, there is a human element that persists: wonder. As the astronomer Maria Mitchell said, "We reach forth and strain every nerve, but we seize only a bit of the curtain that hides the infinite from us." Yet, that bit of curtain has revealed an awful lot, and we continue to gently pull at it. Will we ever see the infinite, or the true beginning, or the full scope of the multiverse? Perhaps not, but the pursuit is part of what makes us human. The same impulse that made our ancestors paint constellations on cave walls and craft stories of creation now drives rockets and equations toward the heavens. Ultimately, the story of the cosmos is meaningful to us because it is also our story. We are not mere spectators. We emerged from this grand process. The hydrogen in our bodies, in every molecule of water, for instance, comes straight from the Big Bang. That means a part of us is as old as time. The carbon in our cells was forged in stellar hearts, making us the heirs of those stars. When we die, our atoms will return to the Earth, and eventually some will drift out to space again, maybe to become part of a new star or planet eons hence. In that sense, we are immortal, though our forms are temporary. So, what does it mean to be born from nothing? It means that existence is a gift against all odds, a tiny realm of something in an infinite sea of nothing. It means that perhaps nothing is unstable or pregnant with potential, that even a void can give rise to worlds. It suggests that reality is not a static block, but a dynamic story. Our universe began in a state devoid of structure, grew into a vast living tapestry, and will either continue to expand and evolve in complexity for some time, or eventually simplify again into quiescence. We got to observe a rich segment of that timeline, full of galaxies and life. That realization can fill one with a sense of reverence, not in a religious sense, but a profound respect for the majesty of nature. As our journey through the cosmos comes to an end, let's reflect on where we are. A small planet orbiting a medium star, on the edge of a galaxy that has at least 100 billion siblings, in a universe of maybe 2 trillion galaxies within our view, each brimming with stars and possibilities, all governed by the same physical laws, all born together in the same primordial explosion, all fated to either drift apart forever or perhaps crash together in some finale. We, ephemeral yet remarkable, stand here and through ingenuity have uncovered this story. It is a continuous, cinematic, emotionally resonant story, one that stretches from the beginning of time to the very ends of imagination. It's a story told by starlight and cosmic background whispers, written in equations and in the awe of anyone who looks up at the midnight sky. It's the story of the cosmos, our story. And though this particular telling of it must now conclude, the story itself goes on, written in the galaxies overhead and the atoms within us. As long as there are thinking beings to wonder and explore, the narrative will be retold, refined and cherished anew. In that sense, the cosmic story truly has no end. It lives so long as curiosity lives. So take a moment to step outside on a clear night. Feel the cool air. Look up. The light hitting your eyes has traversed the universe to reach you. The atoms in your body resonate with the history of the cosmos. The void may be vast, but you carry within you a universe of understanding that fills it with meaning. In the silence of the night, you can hear, if you listen closely, the echoes of the Big Bang and the songs of ancient starlight. The story of everything is speaking, and through our minds and hearts, the cosmos is listening to its own tale. In that communion, between the cosmos and our consciousness, lies a profound truth, that we are not apart from the universe. We are the universe, in small but significant part, and its fate and our fate are intertwined. From nothing we came, into nothing, or something beyond, we may go. But in between, we have the chance to witness and marvel at the grandest of spectacles, existence itself. Let us be grateful for that chance. Let us keep the cosmic perspective, allowing it to illuminate our lives with both humility and wonder. And let us continue the journey, always, for as far as mind and imagination can reach, embracing the mystery and majesty of the cosmos. The cosmic saga continues, and we are fortunate narrators within it. The final line is not yet written.